Hi everyone, can you hear me? Can you please confirm if I'm audible? Okay, so let's get started. As you know, we are going to see this particular topic, which is can you okay? Can you guess the topic? So topic for today is threads, system call, context switch, and this all right. So let's just get started. So please let me know if everything is fine. Audio, video, everything is fine. Just let me know. Okay, in the chat you can just quickly let me know, and we will just start. Okay. Okay. I think everything is great. So let's get started. So this is going to be a marathon session, which means that we will be covering in just one go, one whole topic we will be covering in just one go, and there will be multiple marathons for operating system to cover almost all the topic of the operating systems. Okay. Great. So the books that I will be referring in the marathon or in the lectures that I have referred are these books. Okay, mostly I have referred Galvin, William Stalling, or maybe Tenenbaum. Sometimes I might have referred this three EG pieces. Okay, so let's get started. Now, as per the GATE syllabus, this system called process threads, inter-process communication, these things are there in the GATE syllabus. So we will first be covering this particular system called process threads, which is a major portion. Okay, this inter-process communication, if you want, I can upload one video that I will not take live. Okay, I can upload one video that I have already taught in the classes. So I have already taught in the classes. So I will be taking this particular, I will be uploading this video. But today I will be talking about this. So let's just get started. Okay, because many of the students have confusion in this. And now, before I start, let me just tell you that we will be having, we will be having a link in the description. What you can do, you can watch this video later on. Okay, there is one very nice video. If you just search on the YouTube, the journey of a program, big picture, compiler, linker, assembler, and loader. Okay, just watch this video. This is a just 50-minute video, but it is very important, very nice to understand this operating system little more carefully. Okay, so just watch this video over the YouTube and leave your comment. Okay, definitely watch this video. Now let's just get started with the very first definition, which is a process. So what do you think a process is? Okay, so since it is a marathon, so that is why few concepts. Okay, little bit, one or two concepts maybe I will do. What I will be just telling them, I will be assuming that basics. Okay, very few basics you might be already knowing. So let's just get started with the definition of the process. So as you might be knowing, the process is an active entity, which means a computer program itself is a passive collection of the instructions, while a process is actual execution of those instructions. So basically, process, you will say, is active. Okay, some active entity. Active entity means that it is either running, so it is in main memory. Okay, main memory, or you can say that it is either running or maybe runnable, which means it is either ready to run. Okay, so you can say it is runnable means it is ready to run, which means it is in ready queue. You will get to understand what are these ready queue and all, so don't worry. So let me just get started with the definition of the process. So what is a process? It is a program in itself, which is basically active. So basically, what do you have as a program? See, as a program you have, let's suppose you have some file which is let's suppose a.c. Then what you will do, you will compile it, right? You will compile it, and then you will be getting something like, can anyone tell me what is this? Something like a.assembly. After compiler you will be getting assembly. Okay, and then maybe you will be converting that to a binary after linking. So maybe you need to link it. So see, all of these things I have already talked in this particular video, right? All of this, that what is this linking and what are these things, you just need to watch that video. And then you will be getting a.exe. Now tell me, this a.exe is in your hard disk, this particular thing is in your hard disk or is in the main memory? This particular thing is in the hard disk or in the main memory? This is basically still in the hard disk, right? Still in hard disk. Still in hard disk. So now you tell me, when are you going to run this? When are you going to run this? Maybe after some time, maybe after 5 minutes, maybe after 5 years, right? You do not know. So you will be running this, but maybe after some time. So that's what we say, process, which means, see here, that a program is basically code or maybe some data, which means static data, which means global variables or something, right? Global variable you will be writing. So basically you will be declaring some global variable or maybe static variable or something. So it is a static entity, by the way, right? Now if you run this, which is basically dynamic, you will say that it is running. Okay, if you run this, then it will be having heap, stack, process state, these things. So that is called process. So informally you can say a process is a program is in execution. Okay, informally you can say something like this. So basically you have some program, okay, which is a.exe, which is still in the hard disk. Now if you try to run this, okay, till this point, see, till this point all of this is in the hard disk. Now let me just tell you that what I'm trying to say, that till this point all of this is in the hard disk, and now let's suppose you have compiled it and everything is done. So this compilation and these things are done, right? Now you will load it in the main memory. You will load in main memory, because if you want to run something, that has to be in the main memory, right? If you load in the main memory, then it is called process. Now it is, let's suppose, main memory. Okay, and now you are loading it, then it is called process. This is called now process. Okay, once you load it. Okay, now you tell me one thing, that let's suppose you load it. Okay, which means this is a.exe, and now let's suppose you load it in the main memory. Okay, a.exe or a.out, it depends on that you are on the Windows or on the Linux or so on, right? So but let's suppose you load it in the main memory. Now you tell me, if you load that in the main memory, that this a.exe, right, or a.exe or whatever this is, it will be start, immediately it will start running, or it may be possible that it is in the ready queue, which means the moment you load it, do you think it will immediately start running? May not be, right? It may not be immediately start running, right? Is this okay to everyone? Let me know. Or do you think it will immediately start running? May not be immediately, right? So it may not be immediately start running. So now you tell me, suppose it is not running and you first time load it, okay? Will you call it process, or it is still the program? Will you call it process, or it is still a program? What do you think? See, my question is that when you start, when you load it, okay, using the loader, there is something called as medium term, short term, long term loaders, okay, schedulers or loaders. So we will talk about those later on. But now you tell me that if you load it, so it may be possible that it is not immediately start running. Now the first time you load it, okay, it is not running. Now it is running, and then you can again put in the ready queue. There is something called as ready queue. We will talk about that also. But now you tell me, let's suppose it is now running and then you put in the ready queue, that's okay. But let's suppose it has not got executed even a single time. Okay, so it has, suppose it has not got executed even a single time, but it is still in the main memory. Suppose it has not got executed even a single time. Yet. So will you call it process or not? Will you call it process? So the answer is that it's in the gray area, in the sense that, there are many authors which call it a process. There are many of authors, they say that, okay, as long as it is not even running even a single time, then we will not call it a process, right? So some authors say that it is a process, some authors say it is not a process, right? So that's not very important, but I'm just telling you in case you have the doubt, right? So will you call it a process? Then the answer is that yes. So Abhishek Patel has answered correctly, which means it is in the gray area. Gray area means that some people call it a process, some people do not call it a process. That's fine. Okay, that's completely fine. Now let's just see the definition of the process from this university. What they're saying, the definition of a process informally is quite simple. It's a running program. Okay, it's a running program. Informally, it's just a program in execution. It's a running program The program itself is a lifeless thing. I mean, if you just have a program, they are saying it doesn't have any life. Okay, it is not alive. Okay, it is not in the execution. So it is a lifeless thing. If it is on the disk, that's what they are trying to say. It just sits on the disk. A bunch of instruction and maybe some data. Okay, so maybe some global variable, some static data, and so on, waiting to spring into action. Okay, they want to get into the action. It is the operating system that takes those bytes and gets them running, transforming a program into something useful. So this is the job of the operating system, right? Okay, great. Now you got to understand that you have the program and which is in the hard disk. When you load it using the operating system, okay, there is something called a loader, okay, which is within the operating system. So you can say loader, okay, which is within the operating system. So basically it will load the program somewhere here. Let's suppose this is main memory and this is a.exe, right? Okay, great. So this is the job of operating system, to load it in the main memory. Now let's just move on further. So how to provide the illusion that, okay, basically what may so happen that it turns out that often we want to run more than one program, right? So let's suppose there is a only single CPU. Okay, we want to run more than one program at once. For example, consider your desktop or laptop where you might like to run a web browser, mail program, a game or music player, and so on and so forth, right? So there may be multiple programs currently that is even running on your mobile. So in fact, a typical system may be seemingly running 10 or even hundreds of the process at the same time. Doing so makes systems easy to use, as one never need to be concerned about with whether the CPU is available or one simply runs the program. So here we have a challenge. If there are hundreds of program running, let's suppose you have your music player, you have your web browser, you have, let's suppose, your Zoom, okay, and so on, right? Your Zoom and so on. So if they wants to run on the single CPU, then what do you think that we should do? Single CPU. Okay, this is a single CPU, single core. Which means that will you be running this music player and then this web browser? Or should we provide the illusion that all of them are running simultaneously? See, if this is a single CPU, then it can just execute one of the program at one time. Okay, but let's suppose there are multiple programs. Then can you run them simultaneously, literally simultaneously on CPU, on the single CPU, right? No, right? You can't run. Then this is a job of operating system again, to provide the illusion that there are many CPU. And how to do it? Using something called as scheduling. Okay, so we will be having the round robin scheduling. We will see it later on. Okay, but it's not like that all of them are running simultaneously. All of them are running sequentially, which means first you will run this, then you will run this. It's not like that. So operating system is something which provides the illusion. What is that illusion? It says that, okay, maybe all of them are running simultaneously. As a user, I think that all of them are running simultaneously, but in fact they are not running simultaneously, right? Okay, so we have seen that there are few jobs of the operating system. What are those jobs? Can you tell me? Jobs of operating system. So there are few jobs. Some of them are, you can say, maybe we have just seen that converting a program, okay, program to process, right? To process. Okay, what else? Maybe we have just seen that providing the illusion that there are many CPU. That many CPU are there, right? What else? Suppose that you put the program here, right? You put the program in the main memory. Let's suppose this is the main memory. Now obviously you will be putting multiple programs at a time, right? And one of them is running. Okay, it's not like that all of them are running simultaneously, but there may be multiple processes at the same time. Let's suppose this is running. CPU is currently the program counter. There is something called program counter which is currently at this pointer, which means they are executing the CPU is executing this particular instruction. Okay, suppose that is fine. I mean, CPU can execute one of the program, that is fine. But it is definitely possible that you can't. Let's suppose P4 is coming. Okay, P4 is coming and you want to load it. Can you load it like just randomly at any place? Can you just destroy this p1? Can you just destroy this p1? May not be, right? You may have to load it at some empty place, right? So that's called like, I mean, that's called basically bookkeeping of all the processes. That okay, where is p1, where is p2, where is p3, this area is of p3 area, this area is of p2 area, this area is p1 area. That's called process management, right? Process management. And there are many other, for example, this virtual memory, okay, virtual memory management, in the sense, okay, that is also called memory management, in the sense that okay, p1 memory is this, p2 memory is this, p3 memory is this, right? So memory management, okay, memory management, there are many applications or many jobs of the operating system. So this is also called as memory management. Now just imagine life without operating system, okay? Imagine life without operating system, which means that you just have a CPU. This is your CPU, okay? This is your program. In between that, there is no, okay, there is no operating system which is managing that how this program should be executed on CPU. See, at the end of the day, who is going to execute? Who is going to execute the program? At the end of the day, do you think that I will execute, you will execute, or the operating system will execute? No, right? At the end of the day, CPU will execute all the program. There is a hardware. This hardware is going to run all the programs, right? This hardware. So let's imagine that there is no operating system in between. There is no OS in between. Then don't you think that you manually have to bookkeep that, okay, this program one, let's suppose there is a main memory. Okay, let's suppose these are the let's suppose multiple programs. Let's suppose P1, P2, P3 wants to run, and this is the main memory. Then don't you think you manually, and this is CPU, right? That you manually have to bookkeep that, okay, P1 is here, P2 is here. If there is no operating system, don't you think it is bookkeeping is too much a hectic task? Now just imagine that P1 is using printer, okay? Just imagine P1 is using printer. Now at the same time, do you think P2 can also use the printer? That half of this, some page has been printed, and now half of the content should be of P2. Is it possible? No, right? So this printer, if it is given to P1, then obviously once its job is done, then only you can ask P2 to print. So basically what I'm trying to say, that this is a hardware, right? Hardware, or the resource, you can say this is a resource. So if there is no operating system, then you have to manage the resource. That okay, P1 is using printer, so P2 should not use the printer, right? So there are many things like resource management, bookkeeping, and there are many things that you have to do manually. Is it really a good idea to do all of this manually? See, all of this, whatever we are just discussing, is just daily routine thing, right? Which means routine things. Which means what? Which means that it's not like that once in a while. Do you think that in 1,000 years, or maybe in 1 year, P1, P2, there will be three processes. Let's suppose P1, P3, P4. There will be three processes who wants to run on the CPU, on the same CPU. Do you think it will happen in once in a year? Or you think it's a daily thing, that you will be opening Google Chrome, you will be opening the music player, or and so on, right? Do you think it's a daily thing, or you think it's a once in a year you will be doing that? This is daily routine things, right? So if something which is basically being daily, then isn't it a good idea to write it as one software or one program that does job, all of the job, like bookkeeping, resource management, right? All of this, right? All of this. So you think that isn't it a good idea to write one program that do all of this job: bookkeeping, resource management, memory management, process management, everything, right? Process management, memory management, everything. So if this is happening daily, then why don't we have one program, and that program is called operating system, right? Operating systems. So basically we have just one program that does all of this job, right? That does all of this job, which is called operating systems. Let me know if that is okay to everyone. See, you might have heard about Master's theorem in algorithm, right? Why do we have this Master's theorem in algorithm? Because the kind of recurrence relations, right? I mean, this kind of recurrence relations are basically coming too often in divide and conquer. You will say that, okay, you have divided your job into part, I mean, n by b size, and these are the a jobs. You have divided into a jobs, right? So agent, this kind of recurrence relation are coming very frequently. If these are coming very frequently, then people have said that, okay, let's just do it once, right? Let's not do it again and again. Let's just do it once. So that's why we have Master's theorem. Similarly, if something we need it daily, right? Something we need it daily, then why don't we write? Okay, if this is daily routine things, then why don't we write just one program that will help me again and again? Okay, so that's why we have the operating system. Now, I hope this idea is clear to everyone that why we have operating system. Okay, so let me know if that is okay to everyone. Okay, okay, great. So now let's just get started with the subject, which is operating system. Now you understood what is a process, right? A process is informally a program in execution. Process context means compete compete for the resources, which means some process, let's suppose p1 p2 both might want to use printer at the same time, right? Then we will see that how to resolve that things. Okay, I mean, there might be deadlock, there might not be deadlock. This is the deadlock management in these things, right? Context, there will be a context of a process. What do you mean by that? Context means that a process is currently, let's suppose, running instruction number 3. Okay, so there is something called program counter. I mean, current value of the program counter that is running. There is something called stack pointer, and so on, right? There are, I mean, there are many things that the process is basically currently having. Maybe you can say list of open files, okay, and so on. So multiple processes might be there at the same time. Now, program and process are not equal, which means it is static. It is dynamic, means it is running basically. Okay, one program can create several processes. Okay, we will see that. Okay, using the fork also you can do it. Okay, this is basically one of the example is using fork. We will see that, right? Okay, context of the process means that what it is currently doing. Maybe see, let's suppose it is currently executing this instruction. So what is the program counter value, right? What are the list of open files, stack pointer, and so on? Okay, now let's just have one analogy that see, in the school, let's suppose there are many kids. Okay, there are many kids. Every kid might be doing something of their own activity. So if we want to have a close eye on every kid, then we need a bookkeeping कि ये बच्चा कहाँ पे है ना, right? I mean, currently he is in school, he's outside the school, or maybe what he is doing, what she is doing, and so on, right? So we need to have a close eye if we want to uh, do monitor it basically, right? Similarly, in the operating system, we need to have a close eye on every process. Okay, that close eye is called context basically, which means that what are these values, right? Program counter, stack pointer, and so on, right? That close eye is called context. That what is the current context कि अभी इसका क्या हालत है इस process की. For example, this is process 1, this is process 2, this is process 3. Process 1 might be executing this instruction, process 2 might be here, process 3 might be here. Okay, so basically I'm at this line, and what are the current registers value, right? There will be some registers value, which means that this is basically doing some computation. So as per this computation, what are the registers value, right? So this is, all of these things are called context. Okay, cool. Now, there is a special data structures that keep take care of this keep take care of this context. Can you tell me what is the data structure that has this context? Can anyone tell me what is the data structure that has this context? Yes. So PCB, right? PCB, which is called process control block. PCB is a data structure which basically have all of this. Now, let me just tell you that what is PCB. PCB has the process number, or also called as process ID, which is PID. Okay. What is the program counter value, right? What is the program counter value? What are the general purpose registers? Okay. And I mean, what are the list of open files? And there are many things that it has. Okay, many things that it has. For example, ideally, as per the code, it looks like this. I mean, as per the code, it's just a struct. Okay, it is a data structure which is struct. As per the code, it looks like this. But obviously, you don't need to know this. I mean, you don't need to know that how does it look. But I'm just telling you that as per the code, it is basically a data structure only. Okay, it is just a data structure only. Understood? Now, these are the few entries. I mean, as per the code, it looks like this. So these are the few entries. For example, the size of process memory, that how much memory it is currently using. Okay, size of process memory. There is something called page table. Okay, I mean the outermost page table is also called as page directory or outermost page table. Then what is the page table? I mean page table register. Do you know that page directory? Something like outermost page table. You might have heard, right? I mean that's a part of memory management. We will see that later on. Okay. Kernel stack. Okay, so this kernel stack we will talk today. Talk today. Okay. File, open file, currently working directly, executable file name, which means what was the file name, which means a.exe, or and so on, right? So there are many entries that it has, this PCB. Now let's just see that how to even create a new process which is basically using the fork system call. Okay. So let's just see that this fork system call, okay, this fork system call is very important, in the sense that maybe in every 3-4 years, okay, they can ask one question. Okay, one question from this fork system call. One question. Fork system call. Okay. So if we want to create a new process, then generally in Windows, what we do, generally in Windows, we basically say that, okay, you can just double click. Okay, if it is GUI, not just Windows, basically, I mean in other operating system also, if you double click here, then it creates a process, right? It creates a process. But fork also help us to create the process. Let me tell you how. Okay, let me tell you how. Suppose this is your current process. Have you seen these kind of things before? What is this? Can anyone tell me what is this? This is called virtual memory, right? Virtual memory or logical memory, whatever you want to call. Okay. Which means you have code, data, stack, heap, these things, right? So all of this is called process. I mean, this is called process address space. Okay. So let me quickly tell you that what is this. See. By the way, I will again suggest you to watch this lecture. Maybe it will be really helpful if you watch this lecture, which is this one. Yeah, which is this one. Okay, if you watch this lecture, then it will be really helpful to understand all of this. Okay, I mean you don't need to worry about all of this, but if you still I mean watch this lecture, it will be really helpful to understand that, okay, what is this compilation, how it is getting loaded, and what is this virtual memory, how it is, why it is even needed, right? Why it is needed to know the virtual memory, why it is needed to have this virtual memory. All of this I have talked here, right? Okay. So yeah. So now let's just go back to our slide. So I was saying here that this is called virtual memory or the logical memory, which means whenever you have a process, right? Whenever you load a process, then we say this a process. I mean a process, basically we say it is going to take this much memory. Okay, whatever this memory, we call it logical or virtual memory. Anyone who has watched that lecture here? Anyone here who has watched that lecture earlier? that I just pointed out? Okay. So basically we need this virtual memory. You can just watch that lecture because I have explained very clearly that why we need this virtual memory. Okay. Now we say that okay, there might be some code, there might be static data and so on. And let's suppose this is stack and let's suppose this is heap. So we say that this complete thing is a process. This complete thing is a process. I mean, process is going to run within this, right? This complete thing is a process. Process is going to run within this only. Okay. Now, why we need it? Okay, why we need logical memory? It is also very good explanation. You just watch that lecture because then only you will get to understand. Okay, that why we even need it. Okay, what is this logical memory and why we call it logical? Okay, why we call it logical? You will get to understand very clearly after watching that lecture. Okay. So suppose you have this virtual memory, or maybe you can say process address space. Now let's just see what happens when you invoke a fork system call. Oh, sorry, I mean, don't worry about the system call. We will see here. But when you have this fork, then let's just see what's going to happen. As you can see that using this fork, it will create the exact same replica of this address space. Which means let's suppose there is some variable A. Okay, there's some variable A which is at some memory location, maybe 1000. Now tell me, here the variable A is at which memory location? So this is, by the way, this is called parent. Okay, I mean, one of them is called parent, which is the original one, and another one is called child. This is called parent, this is called child. Okay. Now the parent PCB, okay, there will be two PCB. There will be different PCB for parent and child. Parent PCB will be taking care of this address space. Child PCB will be taking care of this address space. You just tell me one thing, that if A is here at 1000 memory location, then where is this A at which memory location? Can you tell me? Logical address. I'm just asking, logical address is 1000 here. Then here also 1000. Why? Because this is the identical address. I mean, identical copy only. Okay. So this is exactly same copy of this. So logically, if you are storing this as 1000 address, then here also you are storing this as a 1000 address only. Understood? Okay. Now let's just really see that how this fork is working. Okay, I mean, we have seen little bit of this fork. We will see more details of this fork now. So fork, as you have understood, that it is basically creating one more process, right? Something like that, which is just a replica, which is fine. I mean, we can definitely make change here. Okay. And also, like, we can load a completely new program. There is a different system call. Can anyone tell me here what is that system called? Exec, right? Exec. So using this exec, you can completely load a new different program here. Okay. Anyway, don't worry about these things because it's not as per now required, and this is a marathon, so I'm not going to tell all of these things because we have already talked all of these fork and exec, right? All of this in the operating system lectures, right? Okay. So someone is asking that I have doubts, sir, why we use fork just for only for replica. Yeah. So basically we replace this replica. I mean, obviously your doubt is very valid, that why we even need the exact same replica, right? Actually, we don't need it. I mean, we don't need the exact same replica. But what we are going to do, we are first going to have fork, which means we will create the replica, and then we will replace this replica by some other process. Maybe let's suppose it was a.out. You can replace this replica by b.out. Okay, using exec. Okay. I mean, I'm not going to talk about this exec more, but basically you can say that like, whenever I am having fork, after that generally we have exec also, and we will write there, let's suppose b.out. Okay, then what it will do, it will basically create the same process, and there will be a parent which is already having this whole thing. And now we will put a if condition, if that is a child. Okay, I mean, if there is a child, then we will replace this exec will be only in the child. We will replace the child with completely with b.out, and that's how we will create a new process altogether. Okay, so maybe I need to talk about it because there are many doubts that why we even need the replica, right? Okay, so let me just talk about it. Let me just have that particular slide here. Let me just talk about it, that why we need the replica. So if you are by the way, if you are a Go classes student, then you already might be knowing, but still, okay, let's not worry about it. Maybe you are not Go classes student, so that's why you are asking, right? Or maybe you have forgotten, or you might not have seen the lectures. Okay, so just give me a second. This is my hard drive, so I'm just going to plug in this hard drive to get that slide, so that I can just explain this more clearly. Okay, Ayan is saying he's a Go classes student and you already know all of this. That's really great. Okay, okay. So let's just see this. See, let's suppose this is a.c. Okay, this is one file which is a.c, and let's suppose there is another file which is b.c, which is this. Can you tell me, if you run this a.c, then what is the output that you are going to get? If you run this a.c, then what is the output you are going to get? Can you just think about it? So in the a.c, it will say that, okay, you just don't worry about this f plus and all. Okay, in a.c, it will say that, hey, it's a.c, and then okay, don't worry about this. So these things you may not need to worry. This is just to have some syntax correct. Let's not worry about this. And also, let's suppose not worry about this. Okay, so basically what I'm saying, that after this hey, it's a.c, after this we have, let's suppose, this exec. Okay, then what it will do, can anyone tell me what is the output that you are expecting? So basically what it will do, let me just tell you. Okay, let me just tell you what it will do, and then you will completely understand that how it is working. Just give me a second. Okay, okay. So basically how it will work is like this. See here, that there is another system call which is called exec. Okay, there is another system call which is called exec. So how it will work is like this, that we have this. Okay, it will print a.c, then this exec will replace this file completely, which means that was, let's suppose, in main memory it is a.out or something, right? Now what exec will do, exec will say, whenever you have exec, right, whenever you have exec, then what exec will do, exec will say that, see, let's just replace the own process, which means, let's suppose this is a.out in the main memory, it will replace this a.out itself with what, b.out. So it will replace this b.out by this b.out, which means now this process is running. Okay, now this process is running, and that is why now it will never return. So this exec will not return now. So now this hash a.c, it will get printed, and now after that, interestingly, this a.out has been vanished, and now hey, it's b.c, it will get printed. So first it will print hey, it's a.c, then it will print hey, it's b.c, and then it will say that, okay, this exec means it will basically replace by this, and then it will never ever print this welcome back to a.c. It will never ever print this. Okay, so there is a system call which is called exec, which will do what, which will replace its own executable file by some other file. Now why I'm telling you this is because of that basically there is a fork and exec pair. Okay, so fork exec pair, let me just tell you that what does this mean. So you ask me that why we are even basically having the replica, right? So basically, let's suppose this is the current process that you have. Now suppose we have the fork. Okay, which means after this we basically say, let's suppose we have the fork, which means we create the exact same replica using the fork. Okay, there is a fork here, and using this fork, okay, using this fork, we have created the exact same replica of this. So this is the original process that we have. Now there is an exact same replica, which is this, which is a child. Okay. Now what we can do, interestingly, we can replace this child process using the exec, right? So that the parent process is intact, and then we can replace the child process uh, using the exec. So basically, now what we can do in the child process, we can have exec in the child only. Okay, we will not be having it in the child and in a child and the parent both. We will be just having exec in the child only. Okay, so how we will make sure that it is in the child only? We will say that, let's suppose this is a dot out. Okay, in a dot out we will say main. We will say if, okay, I mean, let's suppose int PID equal to fork. Okay, we will say if PID equal 0. Okay, it means, actually I will tell you in a while, that fork returns 0 to the child. So which means if PID equal 0, which means it is a child, basically it is a child. Then replace this, okay, with the exec. So here I have exec a b dot out, right? B dot out. That's all. And whatever code you want to have for the parent, you can have the code, right? I mean, print or whatever, right? So basically now what is the effect of this? You will be creating exact same replica, and one of the replica you will be replacing. This replica got completely replaced. Now why we are doing so? Because that is how we create a process. Okay, so basically let me just summarize this, because if the discussion has been started, so let me just summarize this, that there is a main memory, right? There is a main memory. Now in the main memory, you just have, let's suppose, a dot out. Okay, and now you want to have b dot out also. Okay, b dot out also, you want to have this b dot out also. So what you want to have, you want to basically do it in 2 steps. You will say that, okay, let me make space for b dot out, and let me start running b dot out. So step 1, make space for b dot out. Okay, step 2 is what? Start running b dot out. Now that is how we will create a process. Okay, this process is called process creation. Okay, process creation. Now make a space is nothing but fork. If you have fork, then it will make the exact same replica, and it is still a dot out, right? It is still a dot out. Then if you want to start running, then what you will do? You will do the exec. Okay, you will do the exec. So now it will replace the child only with the b dot out. Okay, now it will say that, okay, let me just replace this a dot out by the b dot out. Now that is how you have a dot out also in the main memory. You have b dot out also in the main memory. Okay, is this understood to everyone, that why we have fork? Because fork, I mean, this is one of the very popular application, that fork and exec pair is used to create the process, create the processes or the process. Okay, is this understood? Let me know everyone if this understood, that why we even have the fork, and why we want to have the identical copy. Okay, so basically the step 1 is that you have just a dot out, you will make a fork, which means you will have now 2 processes. One of the process you will replace, which is a child process. And how you will replace will be only one of the process, just using this simple as if condition. Okay, just this simple if condition, that, okay, if it is a child, then replace. Okay, just simple if condition can replace one of the process. Let me know. So Sonam has asked the question that why do we need to create a replica? Is this clear to you? Okay, Aryan also has asked the same question, that why we need to have the replica. Is this clear to you now? Okay, great. Now let's just move further quickly, and I want to cover many of the things here. Now can you tell me what it will print for the fork? What it will print? Okay. See here, it is a fork. Fork means it will create the two processes. Now for the parent also it will start running from here. For the child also it will start running from here. Now fork will return to child also, to the parent also. To the child it returns 0. So that's why if it is a child, okay, if it is a child, then it will print, child will print this, child will print this. If it is a parent, then parent will print this. Okay. So basically you have here, you have this particular file, and now you just run this, right? If you run this, then what's going to happen? You will say that it will, because of this fork, it will be having the exact same replica. I mean, these are the two programs now, okay? Exact same replica you will be having, exact same. There won't be any difference even, right? There won't be any difference at all. So you have this and you have this also, right? Now, now one of them is parent. Let's suppose this is parent and one of them is child. Let's suppose this is child. Now, if it is a parent, then what is the PID value here? Can anyone tell me what will fork return? PID is not equal to 0. If it is a child, then what is the PID value? PID is 0. Okay. So for the child process, it will print I am a child. For the parent process, it will not execute this. For the parent process, it will print I am a parent. Okay. So it will get printed for the parent. It will get printed for the child. Understood? Great. Now, if it is visible, then you can definitely see here that I am saying, I have even run this. Okay, I have even run in my own computer. It is saying I'm a parent, and I'm a child. Okay, you can definitely see that this is the answer. Now let's just quickly answer me one thing. So if that is the case, can you tell me which one will get printed first? I am parent will get printed first, or I am a child will get printed first? So parent is going to print I am parent, child is going to print I am child, right? Now tell me which one will get printed first. So it will depend on the scheduling, right? I mean, you can't determine it. Maybe parent will get scheduled first, maybe child will get scheduled first, right? So it will depend on the scheduling. Okay, great. Now let's just move further. Just answer me how many times each of this word will get printed, which means how many times this gate will get printed, how many times gate overflow will get printed, and how many times go classes will get printed, how many times ISC will get printed. See, this is gate which is written at first, so one time only. Now you have two processes. I mean, you have two processes. Both of them will be executing from here, right? This remaining portion will get executed by both of them. But if it is a child, then child will print this only one time. And if it is a parent, then it will print only one time. But this will get printed by child and parent both. So two times, right? Two times. Okay. Two times. Is this understood? That gate overflow will get printed by only child. Go classes will get printed by only parent. ISC will get printed two times and gate will get printed one time. Okay. Great. Now let's just move further. Now just answer me this question, that if I'm writing int a equal to 5, printf percentage p means I'm printing address. Okay. This is used to printing addresses. Right? If I'm writing like this, then can you tell me that what does printf print? I mean, the logical address of the variable or the physical address of the variable? Tell me. Logical address or the physical address? What do you think? See, printf never ever print the physical address. Okay. As you can see here from the Stack Overflow, okay, it is impossible even. Okay, it is impossible to get the physical addresses in the standard C language. Okay, so you can't even print the physical address. So it is always logical address. Okay, so it is even impossible. Can anyone tell me why it is impossible? Okay, currently you might not be knowing that what is this physical address and what is this logical address. So let me just tell you what is this physical address and what is this logical address. See, there is a logical memory, right? What is this logical memory? Logical memory is basically something that compiler assume that the program is going to take. And physically later on, okay, later on we can store this anywhere in the main memory, right? Main memory. For example, here A is stored, let's suppose this A is stored at the location 1000. But it may be possible that when you store this complete thing in the main memory, right? Complete thing in the main memory, then you it may be possible that this A might be stored at location maybe 50 here, okay? At location maybe 50. So what I'm trying to say here is that that this is basically the logical address. This is the physical address, right? This 50 is the physical address. So this is the logical address. This is the physical address. Right? No, digital logic is not required to understand this. Okay, you just need to understand the memory management. Don't worry, we will talk about this memory management later on. But for now, you understand that printf always print the logical address. Okay, which means logically, okay, logically, wherever you have stored this A, it will print that, right? Logical address. It is impossible to even print the physical address. Can anyone tell me why? For the security reasons, right? For security reasons. I mean, as a programmer, you should not even know. Okay, for security reason, you can say you should not even know that where is your variable stored. I mean, why do you even care about it, right? Why do you even care about it, that where is your variable stored? Okay, so I hope you understood that what is this logical address and what is this physical address. Basically, this logical address is something that the compiler assume. Okay, I'm see, again I'm saying that that particular video, okay, that particular video, again I will say that if you watch this video, then it will completely get clear that what is the logical memory, what is the physical address, everything will get clear. So I will just request you to watch this video. Okay, and once you watch this video, then let us know in the comment also that you have watched and understood completely. How many of you have not watched this video? Let me tell you that you are missing something great. How many of you have not watched this video? Tell me. Okay, just tell me how many of you have not watched this video. Just watch this video and then it will get completely clear that what is the logical memory and so on. Okay. Okay. Now, as we have discussed that this fork is going to create the identical copy, right? This fork is going to create the identical copy. Now you tell me, if it is going to create the identical copy, now you tell me this particular answer, that if you, let's suppose, run this program, okay, if you, let's suppose, run this program, then child is going to print I am a child, and then it is going to print certain address, and age some variable here, right? Age a variable here. Okay, this is main function, sorry. So age a variable here, and then it will say that okay, I'm a child, and then it will print the address of that variable. It will say I'm a parent, it will print the address of that variable. Now see here, this variable is declared here, and then you are doing the fork. Okay, then you are doing the fork. Tell me, tell me. That what is the answer? Okay. So maybe multiple people are getting different answers, right? Okay. So what is the answer here? The answer is can anyone tell me? Yeah, answer is A. Yeah, that is correct. So let me explain you how. Okay, let me explain you how. Okay. So see here that what is happening? What is happening? That you are having this particular program which is saying see here, which is saying that there is a program, right? Let me just for now let me erase this. They are saying there is a program, Okay, and then you are having some variable a here, right? Some variable, this is in the logical memory. And now you are going to have a fork. You are going to have a fork which will create the exact same replica of this logical memory, right? A, this is again the child. This is child, and it is having the exact same replica of logical memory. Now, what's going to happen is that this a equal to 5, wherever it is stored, let's suppose at 1000, at here also it is stored at 1000. Okay, at here also it is stored at 1000. So basically it is also going to print the logical address, and it is also going to print the logical address, and hence the logical addresses are also same, because 4 create the identical copy. It is the identical copy, right? Since it is the identical copy, that is why you will get 1000 at both the places. Let me know if you have understood this. Okay, see, if you are not getting what is this logical address and so on, so last time, let me just tell you, all you need to do is just watch this video. Okay, just watch this video. And yeah, some people are commenting that that this video is really nice. Okay, so RN is saying video is really amazing. After that video मुझे लगा compiler तो भगवान है. Okay, Dharmveer Singh, I watched it and it was amazing. So please watch this video and comment out. Okay, comment on the video. Comment on video also, so that I get to know that you have really watched the video. Okay, great. Okay, so both are going to print the same thing. That's why A is the correct answer here. Okay, both are going to print the same thing. Understood? Now let's just move on to the next question. Let's just see this question. Can you tell me what is the answer you are getting? They are saying this time they're printing the value. Okay, they're printing the value. This is also printing the value. Now they are saying that this is a fork, and then they are saying that okay, PID equal 0 if it is a child. Okay, I am a child. Child is decreasing, it is increasing, and then what is the final value that they are printing? Tell me. There is something called race condition or the synchronization, but don't worry about it. I mean, we will talk about it in the synchronization. If you don't understand what is this race condition, don't worry. Okay, for this particular question, we don't need it. So here, what they are saying is that if it is a child, then let me just tell you that what they are trying to say. See here, this is very good question, and in fact the same question has been asked in GATE also. Okay, I will solve that particular PYQ. The same question has been asked in GATE also, right? So what they are trying to say is this. Let's suppose that this is your a dot out. Okay, I mean the first program, which is parent. Now you have fork. Then basically you can say it is child. Okay, this was the parent. Yeah, so let's just see that what are the values here. So a equal to 5 is there. Maybe a is stored at some location, but ultimately the value is 5, right? Ultimately the value is 5. Okay, similarly here also you will be getting at the exactly same location this a. Okay, which means logically both are at the same location, which means this is also 1000. Okay, let's suppose this is at the 1000 location, this is also at the 1000 location. Both are logically at the same location. Okay, now let's just see what is going to happen. This is saying that okay, I will decrease by 5. This is going to say I will increase by 5. So if you decrease by 5, let's suppose you are executing this first, then you will say that okay, it will get I mean, if you are executing parent first, it will get increased by 10. Do you think it will also have the same impact? Is this variable shared? That's the main question here. Is this variable shared, or these are the two different copies of the variable? Tell me. This variable a, is this two different copies, or it is shared? Which means if there is a change in first variable, will it automatically get changed in another variable? What do you think? If you change this to 10, will this automatically get changed to 10? That is my question. The answer is no. See, even though interestingly, if you let's suppose printf %p address of A. Okay, here also you printf address of A. Tell me what it will print. It will print 1000. It will also print 1000. Logically the addresses are same. But now let me tell you very interesting story. But physically these are different. Okay, physically these are the two different addresses, which means in the main memory, both are at the end of the day, both are in the main memory, right? I mean, the parent is in the main memory, child is also in the main memory. Let's suppose this is the main memory that we have. Okay, this is the main memory. So we will part in the pages or something. Okay, you will get to understand pages and these things later on. But yeah, you might divide in the pages, but that's okay. But it will get stored somewhere here in the physical location. This is the real thing. Okay, it will get stored somewhere here. Let's suppose it is getting stored somewhere here, right? So this is getting stored somewhere here, right? Let's suppose this is getting stored somewhere here, let's suppose, right? Okay, now you tell me this A5, a which is 5, right? Which is 5. The physically it might be at 2000 location. Physically it might be physically this A physically might be the physical addresses that nobody knows actually, but let's suppose it is 1023, okay, or 1025 or something. Okay, the physical addresses are actually different. Okay, so the physical addresses of both of this A are different actually. Logically they are same, but if you change this to 10, then it has nothing to do. It has nothing to do with this A. Okay, this A, changing this to 10, it has nothing to do with the different A. Is this understood or not? It has nothing to do with this A. Whatever you do here, you are doing actually here, right? Whatever you do here, you are actually doing here. Let me know if that is okay to everyone or not. So here, if you're incrementing in the parent, you're incrementing, right? So this will print 10, this will print 10, you will increment it, this will print 0. Okay, parent will print 10, child will print 0, that's all. They are not the same variable. Although you print them, okay, you print the addresses look same, but actually they are not same, which means physically they are stored at a different location. Actually they are not same, right? Yes. So Sonam is saying this means logical addresses are same, but the physical addresses are not same. So that's the very right line, okay? That the logical addresses are same and the physical addresses are not same. Okay, let me know if everyone understood this. Even I can write it. Okay, I can write it here. So ultimately everything is in the main memory, right? Ultimately at the end of the day, things are in the main memory. So logically they are looking same because it is the identical copy. Okay, because it is the identical copy, that is why they are looking same. Okay, because of the identical copy. But it's like copying a folder and modifying the file separately. Great. This is a very nice example. Okay, so now if I ask you to answer this particular question, let's suppose parent is printing u, which is actually 10, this is 0, then what is the relation between u and b? U is nothing but b plus 10, right? So hence you can say what is the answer here? If this u is basically parent, whatever parent print, this is 0, so I think u equal to b plus 10, so I think b is the answer, right? Okay, great. Yes, so whatever you do at the end of the day, you have to do in the physical memory. At the end of the day, things are stored in the physical memory. Then why we even have the logical memory? Can anyone tell me? Okay, again, you will get to know the answer in this particular video. Okay, why this logical memory make any sense? You will get to know the answer again this in this video. Okay, this is actually required to do the things. Logical memory or virtual memory, whatever you like to say, is the most important and most needed and most amazing invention of this whole computer science, you can say. In fact, in one of the book, it is written that most important breakthrough in the computer science was to have this logical memory itself. Okay. Now now let's just move to this particular question that we have here. Okay, let's just move to this particular question that we have here. What they're saying, this question by the way has got 119 upvotes, which means it is too popular question. Okay, too hard for the aspirants, and 35,000 views, which is too much, right? Okay, now let's just see that what they're saying. They're saying that if 4 equal 0, which means it is a child. Okay, it is a child, and this else will get executed by the parent. Okay, this else will get executed by the parent. U and V are the values printed by the parent process. X and Y are the values. See, they are saying let's just print. Okay, they are saying let's just print. Let me just maybe probably go to the next page. See, okay. See what they are saying, that I hope it is visible to everyone. What they are trying to say. Let me even make it little further visible. What they are trying to say is that they are saying that if 4 equal 0, so they are saying that these are the values, which is this and this. These are the values are called parent. Okay, these are the values which is X and Y. These are the values, let's suppose U and V. Tell me, are the addresses same or not? Are the addresses same or not? Will this U and Y, U and V will be equal, or they will be different? Tell me. Tell me, are the addresses same or not? So what is the correct answer here? Can you tell? This was one of the very hard question on the GATEOverflow. Can you tell me what is the correct answer here? Will they be same? If they are same, then this is the answer or this is the answer. Now you can see very clearly that here if you're having percentage D, then you're printing the value of A, right? Here you're increasing by 5. Maybe earlier value, whatever it is, let's suppose it is 0, or maybe let's suppose earlier value is 10. Okay, whatever it is, doesn't matter. Now here you will print what? You will print 15 and you will print 5, right? So both are actually different copies. Don't get confused that okay this 15 will get decrement or whatever, right? So this is 15, this is 5. So X is nothing but U plus 10. So maybe, yeah, X is U plus 10, right? So what is the answer? C is the answer, right? Great. So congratulations, you have successfully solved one of the very hard question that was on the GATEOverflow. Okay. So once this particular concept of this fork is clear to everyone, that how it is even making the copy. Okay, and these are the identical copy, and printf prints the logical address. Once this small concept is clear to everyone, then everything should be clear about this particular question, right? Everything should be clear. Okay. Okay. Now, basically, like, I mean, I just wanted to share one thing here, which is little, I mean, you might not understand at this moment in time, but that's fine. So, how many of you, by the way, heard about page table? How many of you know about the page table? That what is a page table or something? Anyone? So basically, let me tell you one thing, that how does the fork actually work? Okay, this is, by the way, one optional discussion. Just 2 minutes. Okay, just give me 2 minutes. 2-minute optional discussion. Okay, so how does the fork actually work? What it will do to create the identical copy? It will say that okay, wherever these pages, okay, it will just create the identical copy of the page table itself. Okay, for the page table only. Which means whatever is the parent page table, it will say okay, the exactly same page table I have for the child. Now physically, let's suppose age here, right? Age stored here, which is some value having 5, right? Now interestingly, what happens, that whenever you try to modify this A, okay, let's suppose from 5, one of the process is making it 10. Let's suppose child is making it 10. Then whenever, see, if you're not modifying, then that's okay. But if you try to modify, then it will create a same copy. Okay, if you try to modify this, then it will create the same copy of the page somewhere here, and it will say it is 10, and now it will not link. Let's suppose child is modifying that, it will not say that this is the page table, it will say okay, this is the page table. I mean, it will modify the page table basically. Are you getting my point? See, it will create the copy of the page table only, and whenever you are modifying the value, it will change the page table only, and it will create the copy of that particular process. Particular page table. Okay, somewhere in different frame. So which means it is also called as copy on write, COW. It is also called as copy on write, COW, which means that if you try to modify something, then it will create the copy, which will say that okay, I of child is here, I or a or whatever the variable name you are using, I of parent is here. Now if you modify this I, it will create the same page in some different frame. Okay, it will say I of child is here. Now this page is no longer shared. This is called copy on write, which means whenever you are modifying, then only it will do that change. Otherwise it will not do that change. Is this understood to everyone that what I am trying to say? Anyone who has already seen this process management and these things, is this understood? So that I at least get some satisfaction that okay, whatever I told in last 2 minutes, it is actually conveyed to at least 1 or 2 students. Anyone here who has actually understood that okay, it will create the copy of the page table only, but if you try to modify the variable, then it will say that okay, now this particular page has been copied to somewhere else. Okay, anyone here who has understood this particular concept? Let me know. Okay, so it was just a optional discussion. Don't worry about it if you have not understood. So yeah, some of the students had understood, but don't worry about it. Okay, this was just an optional discussion. Okay, great. Now don't worry if you have not understood, right? Okay, great. So many of you have understood. That's really nice to see that many of you are saying that they have really understood this, right? Okay. So let me just put it. So Sonam is saying, please explain this once again. See what I'm saying. That I mean, there is if you have not understood this page table, then first of all, actually you have to see that what is this page table. But actually, it doesn't create the copy of this particular virtual address space altogether. It will create the copy of the page table only. And later on, if you are modifying some variable, then it will modify it, right? It will basically copy that particular frame only, not the whole all the frames. Okay, I mean, there were two options. Should I copy all the frames and create a new particular page table? Then it is not even required, because for example, code, okay, this code is actually shared. If it is a frame of the code, then isn't it the same in the child and the parent? So why to create the exactly same copy of the code itself? And there are many other frames such that, right? So if you are having any changes, if you are modifying, then only create that copy. Okay, great. Now let's just see this particular question. What is the output of the following program? See, here I want to discuss something called as process graph. Okay, process graph. Let's just see how to solve these kind of questions using the process graph. So see here, you will say that okay, this is, let's suppose, parent, right? This is parent, which is having certain instructions: printf1, fork, and printf2, right? Now this printf1 will print 1, and now whenever you are having fork, you just create one parallel line and copy all these instructions here, which means it will be printf2. Okay, this is child, so this is a parent and this is child. Now printf1 has been printed. Now it will print 2, it will also print 2, and whoever is printing 2 first doesn't matter. So 1, 2, 2 will get printed, right? Yeah, it will print 1 only one time. It will print 1 only one time, and then fork will create the exactly same copy, and which means all the instructions, whatever is written here, you are just going to copy them like this, right? So this is even also called process graph. Okay, so let's just solve more questions and then you will get to understand more. Okay, so it will print 1, and then it is a child, let's suppose, then it will print 2 and 2. Okay. Okay. So now let's just see this. Write down all the possible patterns printed by the following code. So see here, if 4 equal 0, then they are saying print A, otherwise print B, and this is a wait. Okay, this is interesting. This wait is basically waiting for the child. Okay, so it means if it is written in the parent, which means it will wait for the child. What do I mean by that? Let me just tell you using the process graph. See, you will say, see, the instructions that are going to be executed in the parent is this: printf b. So this is, let's suppose I'm writing parent, this is printf b, and wait, and then printf c, right? And then in the child, what it will print? In the child, so this is the parent. In the child, it will execute this statement, which is printf a, and then it will also execute printf. It will not execute this. It will also execute printf c. Now, interestingly, this graph is going to be little directed in the sense that you have this arrow. If there's a wait, then you just have this arrow, which means don't execute after it until unless all of this is finished. So you are going to print. See, you are anyway going to print either B first or A first, right? So what are the possible outputs? Maybe you will schedule this, or maybe you will schedule this. But one thing is for sure: this A and C have to be in the order. Is this possible to print the C and A? Whatever you schedule, okay, don't worry about this C. Actually, this C will happen only after all of this is over, which means this is over, this is over, this is over. Okay, wait means it will wait for the child to finish. So anyway, tell me, is this possible to have CA? No, right? So it will basically have A and C only, but this B may be printed here, this B may be here, this B may be here, this B may be here, right? So once this B is finished, then at the end the C will get printed at the last. So write down all the possible outputs. So how many possible outputs are there? 3 possible outputs. One is BA C, and last C is anyway there, right? Last C is anyway there. Okay. So one is BAC. Another one is this A and C are as it is. This B will be here, right? This B will be here. Another one is this B is here, right? This B is here. A and C are as it is. So these are the 3 possible outputs here, which are possible in this particular example. Let me know, is this understood to everyone? Okay, okay. So understood, right? Great. So are you enjoying this lecture? If you're enjoying the lecture, and if you're getting to know the many new things, right? If you're getting to know many new things, then let us know. Let us know later in the comment. Okay. Later, just put a comment so that other students also get to know that we are really teaching something in depth. Okay. Even in the marathons. Okay. Now, Shakti is saying why 2 C's? Because 1 C is here, okay? 1 C is here also, isn't it? See here, 1 C is here also, and 1 C is here also, and okay, sorry, I thought this is C. Okay. Sorry. So the question that I actually answered is this. No, that is correct. That A and then C. Okay. So basically, this is a process graph. So here I have written whatever parent is going to execute, right? Whatever code parent is going to execute, I have written it. Parent is going to execute these instructions. Child is going to execute these instructions. And this wait is basically saying that wait for the child. Okay. So child is going to execute this and this, right? That's why 2 times C. Okay. That's why 2 times C. Is this understood? Okay. Now, let's just move to one of the very interesting, one of the very not understood, okay, topic, which is system calls. Okay, very less understood to most of the aspirants. Very less understood. Yes, actually, this process graph is really very nice concept. But since it is marathon, I have not gone through much questions. Do you want me to put some questions as an homework for this process graph? Okay, so maybe I can put some questions as an homework for this process graph. Uh, Let me. Okay. So what you can do, you can just answer this question and tell me that what is the answer you are getting. Okay, just answer this and comment your answer. Actually, answer is here on this link. I think currently I don't have the answer, but it can be fine. Okay, answer I have. Okay, answer is on the next page. Okay, answer is on the next page. This is the answer that we are getting. Okay, you can verify the answer later on. Okay, you can verify. So there are many questions, but I think I just have few questions only currently here. But yeah, I can help you few more with few more also. So this is one question. Maybe this is another question that you may want to try, right? Okay. And answer is again, I let me just write it on the next page. Okay, great. So there are many questions we can do using the process graph. But now let's just solve this system calls. I mean, let's just understand the system calls. And actually, this is one topic. This is one topic which is very less understood to most of the aspirants. So we will see this particular topic in very good detail, which is a system call. Okay. So let's just see what it is written on the slide first. I have written something called as user trust issue. So what do I mean by that? Let's just see first. See, most of the users are not expert in computers and do not understand how the hardware works, right? So most of the users are not expert. Do you think you are so much expert that you know each and everything about the hardware? No, right? No. So thus they may not know how to properly manage the resources. So do you think we can trust the users whenever it is coming to manage the resources? Can I ask this users to let the let it manage the resources? Obviously no, right? Because either the user is not expert, or maybe expert or not, doesn't matter, can make incorrect operations while managing the resources also, right? Okay. So user may be malicious also, right? He or she can intentionally make incorrect operations. This can lead to the system failure. So what do I mean by that? What do I mean by that? For example, suppose I want to print hello. Suppose I want to print hello. In that case, do you think that we need to access some resource, some external hardware? Do you think? Yes, right? So what is that external hardware? Maybe you need monitor. You need monitor, right? Right? You need monitor. Okay. So here, this is the hardware that you need. Okay. This is the hardware that you need. Now there are many other examples actually. This is just one example. There are many other examples where you might be needing the hardware, right? So this monitor you might be needing. Now let's just see that what is happening. Monitor you might be needing to print the hello. Let's suppose you want to do a equal to b plus c. Do you think that you need to access I mean, other than the CPU, you need to access some extra resource? If you're just doing a equal to c b plus c, then in that case no, right? Sometimes yes, sometimes you need to access some extra resources. Sometimes you might not need to access some extra resources, right? Sometimes yes, sometimes no, basically. So here, some things, right, some things that we do not need to access the extra resource, somewhere we need. So we do not want the user to directly print on the monitor, which means I should not give a control to user. So who will be handling this? OS, which means I will say that okay, I will request operating system, okay, request to operating system to print this hello. Then operating system will say that okay, I will manage the hardware, I will print the hello on the monitor. The reason is that let's suppose I do not request, okay, let's suppose I directly start printing, okay. So let's suppose I directly start printing. In that case, what will happen? Maybe multiple programs, maybe it is, let's suppose, multiple programs that might want to print at the same time, and you think that that it will get printed successfully. Some other program, okay, some other program might want to print, let's suppose something, maybe let's suppose mobile. Then H will get printed, maybe, and then M will get printed. I mean, sometimes H and then M. I mean, it can garble, right? So that is why we do not trust user. So whenever we need to access the extra resource, there is something called operating system to whom which will we request, and then we will access that particular hardware. Okay, okay. Is this okay to everyone? Right? So we will be accessing the hardware with the help of operating system. Now, what is this operating system? Okay, what is this operating system? Is this a hardware? Just like CPU? It is magic. Okay, it is some dark magic. कुछ काला जादू है. It is some dark magic. It is a piece of code. Piece of code. So what is this? Tell me. It is a piece of code, right? At the end of the day, it is a piece of code, isn't it? So this operating system, sorry, not a dark magic, it is just a piece of code. It is also software, right? It is, let's suppose 10,000 lines of program. Lines of program. Isn't it? It is a 10,000 lines of program. So this operating system is also a program. And then what we do, we say that okay, see here, that we will request the operating system, which is also the program only, right? Which is also the program only. So we say that okay, I don't directly want to print, even I can't print. So maybe I will ask the operating system, and operating system, since being it is a program, it will call some function, right? It will call some function. So this operating system will call appropriate function, and that function is basically in the operating system code. See, this is a 10,000 lines of program, isn't it? So there are many functions, right? In that 10,000 lines of program, right? There are many functions. Maybe let's suppose this is some functions fun one. Okay, there are many functions, right? Sys fun 2. Now whenever I'm having a print, okay, printf, maybe it will be saying that okay, I can't directly do this, let me just transfer my call to something, maybe sys fun 2, okay, something like sys fun 2. So this is also the function. This is also the function, but the only difference is that it is in operating system code. If the function is in the operating system code, we call it not the function call, we call it system call. Okay, we call it system call. So if a function is in operating system code, we call it system call, not the function call. Okay, system call. Let me just explain you what do I mean by that. See here. Yeah. See this particular slide. See here. What do I have here? This particular slide will tell you that what is this function call. I mean, little bit it might be clear, but we will be having more on this function call. Okay, or more on the system call basically. See, you are printing hello. Then it is the standard C library, which is basically this printf hello is the code is written there. Okay, in the C library, this printf code is written. But ultimately, this printf is actually calling the operating system function. Let's suppose the function name is write. Then you will call it a system call. Okay, you will call it a system call. Is this understood to everyone? That if this function name is, let's suppose, write, or any function that is in the operating system code, we will call it a system call, right? So what I'm saying that you have many functions in the operating system code, right? And why those functions are needed? For other purposes. For example, for printf, there is some function or some system call which is needed, right? For many different purposes, you need those, right? Now let me come back to this and I will explain it very properly. See here, that you are basically saying we will be requesting to the operating system, okay, and then operating system will call appropriate function, that is a system call. So that's why I will call it system call. So you are requesting to the operating system will make a system call on behalf of you, and then it will do the job. Okay, so basically there's a user trust issue. That is why we have put the boundary here. Is this understood? We are going to say that okay, this is something that user can do, but if you really want to deal with the hardware, user can just request that I want to deal with the hardware. Ultimately operating system can do. So this is called operating system area, or that's also called kernel area, kernel mode. Okay, kernel. What is kernel? Kernel is nothing but operating system. Basically in operating system you have thousand lines of program, right? But there might be some specific, let's suppose 10,000 lines out of 10,000 lines of program, some specific 1,000 lines of program which are very important, okay, which does very important jobs. So some core of that, I mean you can say core functions, we call it kernel. Okay, I mean there is no specific definition that you need to know, and also there is no specific definition. If you want, you can call complete operating system code as a kernel code, but something which is very fundamental, which is at the center of this operating system code, is called kernel code. So what I'm trying to say here is that you will request operating system will do something on your behalf. So operating system will make the system call, right? Is this understood to everyone? So see, there is a user trust issue. That's why we are putting a boundary, and that's why we are saying that this is a user mode. That's what user can do directly, right? Without the help of operating system. If a equal to b plus c has to be done, do you really think we need operating system for every simple task? No, user can directly execute this on the CPU. Okay, you don't need, okay, once this is scheduled, you can do it. You don't need the operating system help for every simple task, right? But if you want to deal with the hardware, then you need operating system help. Okay, so because there's a user trust issue, that's why we have put the boundary, because we can't ask user to directly deal with this hardware monitor. This is called user mode, this is called kernel mode. Okay, now we might want to ask for the operating system services. So how we will be asking operating system services? Using system call. Okay, so basically this operating system has many functions, right? So let's suppose this is the operating system code. This is operating system code. There are many functions. Okay, there are many functions here. Okay, there are many functions here in this operating system code. Let's suppose this is operating system code. Let's suppose there are let's suppose 5,000 functions. Okay, do you think all of this are system call? In the sense that this I mean there is some associated, let's suppose printf or something that can call any of this function. Actually there are some entry points to this code, which means you can't directly call any of the function, or you can't directly execute any line of this operating system. If you want to get into this operating system code, if you want to execute some function of the operating system code, which is eventually got the system call, that is okay. But if you want to execute some function of the operating system code, then you have to get enter into this, and that's called the entry point of the operating system, which is the system call. So these are the entry points. So that's where you can get enter, right? So these are the entry points. Entry point means system call. Which means if this is 10,000 lines of code, okay, if this is 10,000 lines of code, for example this, okay, whatever this 10,000 lines of code, okay, then you can only enter in this code at the certain entry point. It's not like that कि आपका जो मन में आ रहा है वो पर्टिकुलर लाइन एग्जीक्यूट कर दियो ऑपरेटिंग सिस्टम से, ऐसा नहीं होता है. ओके, यू कांट डू दिस. So there are certain places by which only you can enter, that those places are called entry point or the system calls. Okay, is this understood to everyone that what is the system call? Let me know. Is this really understood that what is the system call? Okay, great. So I think you have really understood that what is the system call, right? I mean, we will be understanding with the more examples, but yeah, mostly you have understood. Okay. So the system calls are the entry points to the kernel, right? So if we want some operating system help, then we will be making a system call, which are the entry points to the kernel. Okay. So as I told you that there is a user trust issue, which means we don't trust users so easily. That is why we need to have two modes here. What are those modes? One is called user mode, another one is called kernel mode. Which means that here, if you recall, that we are saying we can't trust users, so whatever you can do within the user boundary, that's called user mode. Whatever you should do within the, I mean, the operating system can do anything because it actually manages everything. So whenever you need to execute the kernel code, then it is basically has to be done in the kernel mode. Okay, anyway. So in the user mode, compute operations like addition, subtraction, etc, reading or writing into the program's memory, which means, let's suppose you are having a equal to a minus 5, you are writing in the program memory. Let's suppose you are saying a equal to b, you are reading from program memory from this b to a or something like this, right? All of this, do you think that for all of this we need operating system help? We don't need operating system help for all of this, right? Okay, but we need operating system help for IO handling, for CPU and memory management. We will see that what kind of help we might be needing. I mean, what kind of system calls are there, we will see them, don't worry. Okay, so how to ensure that user does not perform something illegal? Before running the instruction, check whether the user is allowed to run or not. This check can be done efficiently in hardware. So basically there are two modes. One is user mode, another one is kernel mode, right? So whenever you're switching from user mode to kernel mode, there is a bit called mode bit, which is actually in hardware. Okay, this is literally in the CPU. In the CPU, this is literally in the chip itself. There is a bit which is a mode bit. Okay, this mode bit that is literally in the CPU, right? If it is one, if the mode bit is one, then you are in the user mode. But if you want to go into the kernel mode, then you put the mode bit at 0. Okay. So let's just move further. So there are some privilege instructions, and for that I need to use kernel mode. For example, CPU maintains a special mode bit, mode equal to 0 in the kernel mode, otherwise in the user mode. Instructions that are considered critical will run only in mode equal to 0. For example, changing the value of program counter. Okay, so if you want to change the value of program counter, then you have to use which mode? Kernel mode. Can you tell me why modifying the program counter need OS help? Is privilege instruction. Why modifying the program counter is basically privilege instruction? Why that is the case? Can anyone tell me? See, see, let's suppose, just imagine a case that we are allowing, okay, just imagine a case that we are allowing user to modify. Okay, just imagine the case we are allowing user to modify the program counter. Do you think it's a good idea? Do you think? Obviously no, right? Obviously no. And why that is the case? Why that is the case? Why should not we allow user? Privilege instruction is something which can be executed only in kernel mode. Can be executed using can be executed only in kernel mode. Because maybe user can modify it to some other user memory. Okay, it might want to access some other user memory. That is why modifying the program counter is not I should not allow user to modify the program counter without the kernel mode, right? So kernel should know. Basically, let's suppose for example there is a memory, right? And my program which is a dot out, maybe it is in pages, maybe here and there, but let's for simplicity, let's suppose my program is here. Okay, my program p1 is basically, let's suppose, here. And this program counter value maybe let's suppose p2 is here, and I may say that program counter value should be here, which is, let's suppose, 3500. Okay, can I say, should I be allowed to say that, okay, now the PC is 3500? Should I allow to say this? The answer is no. The reason is very obvious, because if I allow to say this, then I'm actually able to execute some different code, okay, other than me, and I should not even able to look at beyond me. Okay, see, whatever the address space I have, right? Whatever the address space I have, this is called address space. Whatever the address space I have, I should not be allowed to look beyond this address space. Okay, I should not, as a user, okay, user should not execute, should not be allowed to execute other than this address space, right? Address space means this logical memory. Okay, so that is why I should not modify. So I should not be modifying. Tell me, do operating system know that 3500? If I want to modify, then I will be taking the help of operating system. Tell me, will operating system allow this to modify to 3500? Do operating system really know that 3500 is not in P1 boundary? It is actually belonging to some other processor. Do operating system know that this program counter 3500 is actually this particular address belonging to some other process, not P1? Obviously, operating system knows about every process. Do you remember that analogy of school and child? Okay, in a school, let's suppose if I want to keep close eye on the child, then I will be basically, I want to maintain the bookkeeping, then I can keep a close eye on the child. Similarly, operating system keep a close eye on every other process, right? Okay, operating system maintain everything. So obviously operating system know that, okay, this is something wrong. Okay, so operating system will not allow, even though a user request, operating system will say fail. Okay, request fail. Okay, the permission is not granted, something like this. Understood? Okay, great. So there are some privileged instructions that I should not allow. There are some instructions like, for example, a equal to b plus c, I should allow in the user mode. Changing the program counter value, I should not allow in the user mode. Okay, so if I want to change this program counter value, then what will happen? I will ask the operating system, oh operating system, help me, and operating system will make a check. Okay, this should be allowed or not. Maybe I'm setting to some value which is not allowed. Operating system will say, okay, granted or maybe not granted, right? Understood? Great. Now let's just see this Stack Overflow answer, which has got 171 upvote on the Stack Overflow, which is a huge upvotes on the Stack Overflow. On the Stack Overflow, even the 10 upvotes are very good, and this 171 upvotes, this is huge, right? So let's just read it. What they're saying. What about the kernel mode? What about the user mode? Let's just quickly read, because this is one of the very popular answer on the Stack Overflow that I've taken. So they're saying in kernel mode, the executing code has complete and unrestricted access to the underlying hardware. So in the kernel mode, you have complete and unrestricted access. Okay, you have complete access. It can execute any CPU instruction and reference any memory address. Kernel mode is generally reserved for the lowest level, most trusted functions of the operating system. Crashes in kernel mode are catastrophic, which means if there's a crash in kernel mode, then the entire PC you have to shut down. Okay, I mean there is no recovery generally. In the user mode, the executing code has no ability to direct access the hardware or the reference memory. Code running in the user mode must delegate the system APIs to access. I will tell you what does the system API mean. Basically, this printf, right? Printf. Using the printf, I am making the request, right? So as per the user, this is very high level program that I'm writing in the user mode. This is called API, application interface program. Okay, this printf is basically a part of API only. API means the library function called, okay, the C library or something, library function, that's called API. So basically in the user mode, they are saying that code running in the user mode must delegate the system APIs to access the hardware or the memory. Due to protection afforded by this sort of isolation, crashes in the user mode are always recoverable. So basically, let's suppose there's some programs, some program is getting crashed, some user program is getting crashed, and that is still in the user mode. Then operating system will say that okay, you are getting crashed. Let me just schedule something else, or maybe let me just terminate your program. Okay, operating system can definitely recover it. But let's suppose जो रिकवर करता है, फॉर एग्जाम्पल ऑपरेटिंग सिस्टम खुद ही फेल हो गया है ना, उस टाइम पे लाइक कर्नल के ही कोड में दिक्कत आ गई, विच मीन्स सिस्टम कॉल मैंने किया एंड कर्नल मोड में ही कुछ प्रॉब्लम हो गई, तो जनरली दे आर नॉट रिकवरेबल. ओके, एनीवे लेट्स नॉट वरी अबाउट इट मच. Okay, so just to summarize that what is the system call, it is saying that note that we have blocked users from doing certain tasks to protect the illegal use of the system. Okay, so instead user can user will now request operating system to perform these tasks. These tasks will run the privilege instructions. So for example, if I want to set the PC to 3500, then what will I do? I will ask the operating system. For example, if I want to printf something, I will ask the operating system, right? User program can initiate such request. It can request the operating system using the mechanism of system calls. Note that we need to change the mode here. Understood? Okay, let's just understand this even more carefully. Okay, let's just understand to this entirety. Okay, what the system call is. Let's just understand this to completely, that what the system call is. Okay, so that you never forget, or any question that comes into the gate, you will answer extremely confidently that okay, this is the what the system call is. Okay, anyway, this particular slide I have taken from Galvin. See here, user is doing something, suddenly needs to have the print or maybe something which requires the operating system service. So you will call the system call and mode bit. Okay, here the mode bit is 1. So mode bit will set to 0. It will execute the system call and it will return, right? This is the high level thing that is happening here. Okay, mode bit is 1 and 0. Now see here, this invoking system calls. Okay, I have taken the slide from Washington University. So what they are saying, let's just read it out. A process cannot invoke a system calls like regular functions because they are part of the kernel space. Okay, so it's not like a regular function that will be calling it. For example, let's suppose in operating system code, there is a function. Okay, there is a function which I am calling sysfun. This is within the operating system code. Okay, do you think as a user, I can directly call this function? Do you think? No. I will be maybe having printf, I will be having the library, it will request operating system to call this. Okay, I can't directly call this. I will tell you how it actually happens. Okay, it actually happens using the API. So modern CPU provides a special instruction called software interrupt, which can be performed user space software. Okay, so which are called API. So let me just go over to some slides. See here, what is the difference between system call and the function call? Function call is within the same process. Okay, system call is basically this is the process and you are calling the operating system code. That is the system call. Is the slide understood to everyone? Each of you have understood the slide very clearly or not? Let me know. Each of you. Okay, Each of you should understand that system call is calling a different function from the operating system code. Function call is basically calling its own function. Understood? Okay. Okay. Great. Now let's just see this system call. Okay, let's just answer this. This is a question that I would like to ask you. Tell me what is the correct answer here. Tell me what is the correct answer here. System calls must be used to modify the global variables. Do you think if I just need to modify some variable, some memory equal to a plus 1 or something, I need a system call here? Tell me. No, right? No. So I don't need this. I don't need to modify. I don't need a system call to modify the global variables. Call a user written function. If it is a user written function, do you think I need a system call here? No, right? Write to a file. Yes. Why that is the case? Yes. Why? Because if let's suppose there's a file, and then if a process wants to P1 wants to write to this file, then it may be possible that this P1 should not be allowed to write the file, right? So it will request operating system that, see, I want to execute or I want to write some file. Okay, I want to write to this file. Then then operating system will check, okay, is this file having the permission, no, for this particular process, or this process is having a permission that, okay, to execute this file or to write something on the file. If the permission is there, already there, then the operating system will allow. Otherwise, operating system should not allow. So this request have to be made through the operating system. It's not like you can directly write to a file, right? Otherwise, it will be a huge problem. Let's suppose, for example, let's suppose these are the multiple files. File 1, this is file 2, this is file 3. Let's suppose these are the multiple files, and this P1 is, let's suppose, is a malicious function, okay, is a malicious program. And if I directly allow, then what it will do? It may corrupt this, may corrupt, right? May corrupt some file. Hence, should be checked using operating system before modify. Should be checked with operating system before modify, isn't it? Okay. Great. Now, let's just see system call execution, which means how it actually get executed. Okay, system call execution. Let's just see this. So here we just need to quickly see one thing that is called system call in assembly. For example, let's suppose that you write, just a second, yeah. For example, that you write a fork. Okay, fork is also a system call. Why it is a system call? Because it is creating a process. Okay, creating a process, which means it is having something to deal with the memory, right? So fork is basically, generally, this fork. Okay, so there is one more instruction, which is, let's suppose, REI. So this fork, whenever you write this fork, actually this fork, this looks like this in assembly, which means this fork, whenever you write this fork is nothing but these three. Generally almost all of the system calls are these three instructions in assembly. Okay, this is a fork in assembly, right? Now what is happening here? This is one instruction, this is another instruction, this is another instruction. So what is this? Let me just tell you. See, this instruction is saying move this 57 to some register which is RAX. Okay, maybe there's a register which is RAX. Move this 57 to this register, and then there's a sys call. There's some instruction called sys call. Now what the syscall will do? This syscall will basically there is something called, have you heard about interrupt service routine and these things? So let me tell you, there is something called system call table, okay, or interrupt table. Okay, interrupt table, or I can also call it system call table. Okay, in our case I can call it system call table. So what is this table? It will be having some numbers, for example 0 1 2 3, and for example 57 is here. Okay, it will be having some numbers, and there will be some addresses. Okay, address of the line to be executed, which means it says that if I'm having 57, corresponding to 57 there is some line, or maybe the first line, the function actually, let's suppose corresponding to 57, I want to, let's suppose this is some function which is maybe create or something. Okay, maybe some function within the operating system code. Okay, now at this 57, whatever the address is written, it will go here and it will start executing this function. So basically, if I'm writing move rx 57, then what does this mean? It will put this 57 into rx, and then this syscall will do what? This will do one thing. It will say that, okay, now let me go to system call table. Okay, now execution is transferred to system call table, and then operating system will load the value from here 57. Then it will say, okay, in the system call table I will go to the 57th row, and I will do whatever, wherever it wants me to do. Okay, it will say that, okay, call this create function. Then it will create some process or something like that, which is an actual system call, which is an operating system code, right? And then it will finally return to this particular instruction. And then this rei means just setting the bit from, see, like whenever you start executing this, right, whenever you start executing this, before that you will set the mode bit to 0, and rei will just set this mode bit to 1. Okay, it will just set this mode bit to 1 again. So what is happening? This fork is basically just nothing but the 3 instructions, which is saying that, okay, in the interrupt service routine, or maybe in the interrupt service table, or you can say the system call table, go to the 57th line. Okay, which means that operating system with this syscall will do what? It will say that, okay, I will go to the 57th line in the system call table, and I will set the mode bit to 0. It will start executing wherever this 57 linth number will ask me to execute, right? And then I will return here. Then this rei will say that, okay, now let me set the mode bit to 1. Okay, so any system call in the assembly language is like this. Any system call, which means it will be some instruction, then syscall, then rei. Okay, the number will be different. Okay, for fork this number is 57. Maybe for printf, okay, maybe for printf, because it is also calling one system call. For printf this number could be different. Maybe for printf you can say, okay, for example, for this printf, maybe the number could be let's suppose 30. Okay, something like this. The only difference will be that number will be different. Okay, let's suppose for printf, this number could be 30, something like this. It is understood that how actually the system calls are working. This is nothing but, if we have seen interrupt in the computer architecture, the interrupt and the system calls are exactly same. Okay, the behavior is exactly same. 57 is just a number. Okay, 57 is just a number. It will go to that number, and then whatever the address, okay, address of the code will be written here. It will now go here. It will start executing this function. Understood? So that is how system calls are actually getting executed. Okay, that is how the system calls are actually getting executed. Now I hope you understood that the system call in assembly, this is I have taken from Stack Overflow. They are saying that this is some, okay, trap, or maybe syscall or something. Okay, or maybe syscall. I mean, it will depend on the architecture, that what is the exact syntax, but at the end there will be rei or something. Okay, no, 57 is not the program counter value. It is just a value which index the system call table or the interrupt table. And the program counter value is this actually. Okay, the program counter will set to this. This is the program counter value. 57 is not the program counter value, right? It cannot be set 0 by the user. So it is hardware, so setting the value can be done only physically. No, you will be moving to the kernel mode, right? I mean, basically you can say that after moving to the kernel mode, like once you call the syscall, after that you will be in the kernel mode, and here you will be modifying this mode to be 0. Okay, so once this mode is 0, then you will be executing the actual system call, and then you will be returning here. Okay, so the overheads, as you can see, for the system call are very system calls are very slow. Why? Because changing the protection domains, validating the arguments. Okay, what was the 57, which means, for example, 57, and there may be other arguments also. For example, printf, whatever it wants to print. Let's suppose hello, it wants to print hello. For example, this hello is one argument, right? Adjusting memory mapping, and there are many things that you need to do. So that's why the system calls are very slow. Okay, program should make a few system call, as few as possible, basically. Now, as you know that this is user space, kernel space, and in the kernel space only we deal with the hardware, right? So what is a system call again? It is there are various possible answers from different perspectives. Okay, let's just see those possible answers. So one answer is that is request to the kernel to perform a service. For example, open a file. Okay, this is a system. I mean, this is one perspective, basically, that we are requesting to the kernel to perform a service. That's what I told. I mean, this is one perspective I told you, right? That if we want to do something, we will be requesting operating system using the system calls, right? This is one possible perspective. Another possible perspective is, okay, we are calling a function. That's also I told you. Okay, that's also I told you that this is another possible perspective, calling a function. That function is basically, okay, syscall looks like another function call. It is basically, you can say it is a library function, but ultimately it will get converted into something like that, move rax comma something and something like that, right? So here some, as a programmer I can say it is a system call. Okay, as a programmer. Okay, as a programmer I can say this is a system call, which means ultimately it will execute something within the operating system code. The different perspective could be that it is an entry point. Do you remember I told you that there are certain entry point only? So another perspective could be this entry point also. Okay, so there are many perspectives, right? There are many perspectives. I mean, there are 3 to 4 perspectives at least, you can say, for the system call. Some people say it is just like a function call. Ultimately, you will be executing operating system code. Some people say, okay, if I want to request some service to the operating system, I will be using system call. Some people say it is just an entry point. Okay, so there are many possible perspectives of the system call. Okay, I think, yeah. So this is system call table. I think these things are okay as per the marathon. Let's just answer this question. System calls are as fast as function call. What do you think? It is question from Harvard University. System calls are as fast as function call. So what is the answer here? Obviously no, right? Because in function call you don't need to change the bit, you don't need to take care of anything else. So that's why system calls are not as fast as function call, obviously. Okay. Sorry, this is false. So this is false. Yeah, this is false. Can you see the answer here? Okay. So what are the different type of system calls? Maybe you can have fork as a system call, exec as a system call, right? These are for the process control, maybe to create the process. There is some system call called kill. Okay, if you want to kill yourself, I mean kill your own process at least, right? And there are many system calls which are related to process. Systems calls, for example, related to files. Okay, system calls related to device, system call related to get time, I mean what is the system time and so on, set time and so on, right? There are many system calls. For example, these are the few system calls that I have written in the Unix. Okay, I think in the Unix there are more than 400 plus system calls. There are few I have written here. Okay, there are few which, for example, fork, exec, these things, right? These are the few system calls I have written. Okay, and system calls is not just limited to Unix or something. It could be also in the it could be also in the Windows, right? Because in Windows and Linux it doesn't matter. It is a concept of the operating system, not a particular operating system. Okay, now let's just see a new topic, which is threads. Okay, so basically this topic will take maybe maybe two more hours. So you think we should continue here, or we should continue in a different in a different session? What do you think? This is a very nice topic. I want to talk about this, that what are the kernel level threads, what are the user level threads, and there are a few things that I want to talk about here, and the kernel stack, user stack, these things, right? And then finally we will talk about some of the very popular gate PYQs. Okay, some of the gate PYQs which are dealing with these system call, thread, kernel thread, these things. So what should we do here? Okay, so maybe we can do one thing. We can have one more session, okay, in the morning. Okay, and then we can understand these threads, right? So let me schedule one more session for the morning, right? Okay, so this is actually very important point, important topic that I want to discuss. So we can talk about this in the new session, right? Cool. Great. Or should I take 10 minutes break? I'm not sure. Okay, let's do one thing. Let's just continue with the session, maybe. Okay, let's just continue with the session. So let's just have 5 minutes break, 5 or 10 minutes break, and then we will meet, right? So meanwhile you can take some rest. So it's just a 10-minute break. Okay, hi everyone. I hope you can hear me right. Okay, Dhruv is saying that hello sir, I have taken Go classes test series, but I am only getting 40 to 44 marks in every AMT. So I think Dhruv, it is really good marks. I mean, in our AMT, if you're getting these many marks, then it is good marks. So to improve, I will suggest you that just have a proper revision, and most probably after the revision, you will be able to improve your marks, right? So have a proper revision and attempt the questions with the focus. Okay. So now let's just get started with this new topic, which is threads. So let me know if you all have joined, and so that we can start, right? Okay, great. Let's just get started with this threads. Now, suppose that you want to, in certain situation, there is a single application that may require several threads. Suppose that you have the word MS Word, okay, MS Word, Microsoft Word that you have. Then you are writing some program. Then obviously you have opened the text editor itself, which is itself a program. I mean, that itself is basically some program that could be the program, and maybe there's a spell checker. You are also checking the spell checker, and so on, right? Now you tell me, is this a good idea to have these two as a different programs, or can I have different threads? What do I mean by that? Let me just tell you. Okay, what do I mean by that? Let me just tell you. See, if we are having these two different programs, then it's not a good idea. Why? Because there are many things which are common in the text, in this text editor and the spell checker, because both are working on the same file, right? So there could be many things which are common in this. So there are many things which are common in these two programs, right? Which are common in these two programs. These two programs. For example, both are working on the same file. So it may be a good idea, right? So for example, both are working on same file. So it is a good idea to make these two as a different threads, not as a program. Okay. So we will, if something is common, then we will make these two as different threads. So we will make these two as different threads. Is this okay to everyone? Not the programs. Let me know. Let me know if that is okay. Right? So let's just respond that why do we need a thread? Why do we need thread? Because if there are two programs which are of similar nature, most probably, okay, which are of similar nature, then we might not need to basically we might not need to use two different programs. We can use two different threads. Let me tell you that what is the benefit of that. Okay, let me tell you. See, let's just see that what are the threads. So let's suppose this is a single threaded process and this is a multi-threaded process. So what are the differences here? If you have noticed that in this single threaded process, we basically have just one thread, and there will be code of the program also, or the process also, right? Data also, files also, in which it is dealing with the registers, general purpose registers, program counter, stack pointer, and these things, right? And the stack, and there are many things that each program is having, basically, right? So all of this are being used just by a single thread. But let's suppose I create multiple threads, which means I say that, okay, this particular program might be having multiple threads. Then if you have multiple threads, then you just tell me that what are the things that will be shared between these two threads. Okay, what are the things that will be shared between these two threads? What do I mean by that? Let me just tell you. See, let me let's suppose there's a main function. In this main function, you will create, let's suppose let's suppose p thread. There are libraries. Okay, I will tell a little bit about it, but let's suppose you are creating some thread. There's a library p thread. Let's suppose you create some thread and you execute, let's suppose foo is a function, or maybe some other function. You are calling some function foo, which is here, right? Foo. Okay. Let's suppose this is maybe fun. There is another function fun that you are basically executing. This is just a C syntax. You don't need to worry about the syntax because that's not required for the gate. I'm just telling you that using the libraries we can create the threads and we can execute. And let's suppose this is another thread, and then we are executing some other function, which is, let's suppose, fun. Okay, let's suppose fun. Okay, fun. So this, let's suppose this is T1, this is T2, which means this T1 is executing this function, this T2 might be executing this function. And you can do many other things. Okay, you can do thread join and many other things you can do. But let's suppose this is a minimalistic code that I have for the two different threads. Okay, now it is using this function, it is executing this function. Now you tell me, are these two threads, okay, if these are the two threads, are these two threads executing within the same code, which means ultimately the process is same, or there are two different processes? You just tell me. So the process itself is at least same, right? This particular process is just a one process, so it is the same, which means it is called process address space, which means both the threads are within the same address space, right? Threads are within the same address space. Is this okay? Threads are within same address space. Address space means they are within the same program. Now obviously they are executing the same code. I mean, for example, executing the same code means, for example, here is a global variable int a equal to 5. Tell me, can this function use this global variable? Right? This function can also use a global variable. This function can also use a global variable. Since both the functions can use the global variables, so I can say if these are the two different threads, then the global variables are basically stored in the static area, if you remember. Then these two threads should share. So let me just ask you, what are the things that threads should share? Okay, threads should share. What are the things that threads should share? Can you tell me? Maybe the code they should share, isn't it? What are the other things that they should share? The static area, right? Tell me, can they share the stack? For example, there is one thread which is executing this function foo, and this is having some computation. Okay, this is doing a equal to b plus c, which means this is putting I mean, maybe it is, let's suppose, having int a is a global it is a local variable here, a is a local variable here. Now tell me, is this possible for threads to share the stack? Which means if this is basically pushing a in some stack, then maybe there's a fun which is having b, right? Which is having b. It might be putting b in the some stack, and see here that this function should know that, okay, this I have put, I mean, this has put like I have put b, and there is no one else. I mean, it should know that, okay, how much down I should go to access this b, right? If let's suppose some functions or some threads are using the same stack, then what is the problem here? The problem is that let's suppose this is a, b, these are by the thread 1, and let's suppose c is by thread 2, and then maybe d and e are again by thread 1. Then do thread 1 know that, okay, thread 2 has already put c, then I should not I mean, go here directly to b, or I should go here for b? What I mean to say, that this thread should be knowing that how much go down to get the b, right? So if some thread is putting so some thread, maybe t2, okay, so see, this t1 should know that how much to go down to get this b. If t1 is putting something in the between, then t2 is putting something in the between, then t1 will get confused, right? So the stack should not be shared. Okay, in stack basically we put the local variables of the function. I mean, there are many other computation that we can do. So stack should not be shared. Why? Because otherwise the threads will get confused that how much to go down. Okay. Okay. So now what I'm saying here is that things that should not be shared are, okay, so these are the things that we should share. And I mean, we mean thread, right? Things threads should not share is stack, right? They should not share stack. Okay. Okay. And what else? What else they should share? Basically, they also share heap, right? They also share heap. You think they should share the registers? No, right? Maybe it is modifying, one thread is modifying some register, and then the other thread should not be directly accessing the registers. I mean, the registers might get be modified differently. So they should not share this, right? Should not share this, which means each thread has its own set of registers that it is working with. Each thread is basically has its own stack, and code, data are the files, okay, these are shared. And heap also, right? Heap is also shared. Let me know if that is understood. Okay, maybe little bit it is understood, not very much, but little bit it is understood. Now tell me, if this is a single thread, then how many stacks you have? Just one stack. If this is three threads, then you have three stacks. So how it will look like? See, if it is just old process address space, means it is just one thread. But if you, let's suppose you have multiple threads, then there will be multiple threads, multiple stacks, right? It will look something like this. Just one heap, one code, one static. All of this is shared. Okay, all of this area is shared, but stack is not shared. Okay, because they can run interleaving fashion. So someone is pushing A, someone may push B. So let them do in their own space. Okay, in their own stack, right? Okay, now you tell me very interesting thing. Can can any thread, let's suppose the thread which is thread 1, okay, can thread 1 and thread 2 both access the heap? So suppose in heap there is a variable, there is a location 1000. Then tell me, then can T1 and T2 both access this? What do you think? Answer is yes, right? Because heap is shared, so they both can access. Okay, answer is yes. Now you tell me, suppose, okay, suppose there is some variable A. Okay, suppose some variable A is in T2 stack. Then you tell me, then can T1 access this variable? Can T1 access this variable? Let me know. So I'm just asking if T1 can access the variable. Okay, you just need to tell me if some variable is there. You just need to tell me if that variable can be accessed by other thread or not. Okay, okay. So let me just tell you that, see, both of them, okay, see here, the both of them, right? The both of the threads are in the same address space, isn't it? So tell me, is this true that both of the threads are in the same address space? So since they are in the same address space, then why not? Okay, they can access. Okay, at least they can access. Okay, see, the thing here, this is a very, very tricky question, and most of the aspirants say no. Okay, so most aspirants say no here. But let me just tell you, the real answer is yes. See here, this is from the Berkeley University. Okay, from this Berkeley University, what they're saying, this Berkeley University. Okay, someone last in the last session, someone said when I was solving AMT questions, so someone in the last session said, "कि sir एक बार Berkeley बोल दो." Okay, and there were many questions from Berkeley in that AMT itself. Anyway, so see here, threads within the same process can share the data one another by passing pointers to object on their stack. So basically, on their stack, if there is some data, okay, they can share this data. Anyway, they can share this data because both are within the same address space. Okay, but real answer is yes. Why that is the case? Because both are in the same address space. ये पूरा एक ही है ना? Because both are in same address space. See, why we had different stacks? Just to not get confused कि यहाँ पे A push हुआ है. For example, if some thread has pushed A, okay, some thread has pushed A, B, and then other thread has pushed C. So I should not be confused that it is my variable or it is someone else's variable. For that purpose only I have the different stacks, right? So let me work with my stack. You work with your stack. We will not get confused. But for example, let me write a code and let me just ask you here. Let me just ask you. Suppose that you have something like this. For example, you have foo, and then this is having int a, okay, int a, and then let's suppose it's return address of a, okay, or maybe you can have something like this. You can have int star p, okay, and here p equal to address of a. Now tell me a thread, okay, let's suppose t1 is basically calling this foo, okay, t1 is calling this foo, t2 may be calling some other function, and then in that function fun, okay, in that function fun, can't I use this p, I mean can't I use this address in that function using this p? Maybe if I'm passing that address, then maybe I can do star p equal to 0, isn't it? Maybe I can do this, right? If I'm allowed to pass this address, if somehow if this function or this thread, okay, this thread and this function is same in this case, which means these two threads are executing different functions. If somehow this thread is having the address of the local variable of this thread stack, somehow, okay, maybe by a global variable, maybe someone is passing, but somehow if I'm having, let's suppose I'm working with my stack, but somehow I want to access this, will this be illegal to access? That's what I'm asking. Okay, so this is not illegal to access. Okay, this is not illegal to access, right? Basically stack area is divided, separate stack area for different threads. Yes, there are separate stacks for the different thread, but it doesn't mean that if some thread t3 wants to access this or modify this, then they can do it. It is just for our feasibility we have divided it. It doesn't mean now it is illegal for this thread to access this A. Is this understood? Okay, is this understood to everyone? Let me know. It doesn't mean that T3 can't execute this or can't access this. It is just for our feasibility we have divided it, right? Okay, so they are in the same address space. That is why they can do it, right? They can do it. Okay, great. So you see here, this is true. Okay, this is true. And many aspirants may fail to answer this. Many aspirants may fail. But this is from Berkeley University. So I hope you understood that this is true, right? Let me know if there is any problem. Okay, okay. Now let's just solve a next question which has been asked in GATE 2017. Okay, actually that question has been asked in my set. Okay, when I appeared in GATE 2017, then this question was asked. Can you solve this question? Threads of a process share global variables, do they share, but not heap. No, heap they share. Global variables they share, means static data they share. Heap, but not global variables. No, static data also they share. Neither global variables nor heap, both heap and global variables. So what is the answer here? What is the answer here? It is definitely D, right? It is definitely D. Okay, heap and global variables both are shared. Great, easy question only, but yeah, I hope you understood. So is this okay to every one of you that stacks are different? It doesn't mean it is illegal for this thread to access this some variable, right? Okay. Now let's just see the type of threads. Okay, what are the different type of threads possible? So there are two popular type of threads, which is user level and this is kernel level. Let's just see these two type of threads, which are actually very important to understand also. Let's just see. So what are the user level threads? Okay, whenever we are making the threads using some function calls, then we call it a user level thread. I mean, I will tell you more detail obviously, but just understand in the oversimplification way that okay, if the threads are being called, are being created using a function call, then it is user level. If they are being created using a system call, then it is called kernel level thread. Okay, so let's just understand more. Okay, let's just understand more. So how to create or how to initiate these threads? For the user level, there are some libraries. For the kernel level, there are some libraries. You don't need to worry about. Okay, there is some library pthread. Pthread, you might have heard in the Linux there is some library pthread. You don't need to worry about. I'm just telling you that there are some libraries which help us to create user level thread. There are some libraries which help us to create kernel level thread. Okay. See, this is a screenshot from Galvin. Okay. So maybe I can quickly read it that what they're trying to say. This is a screenshot, by the way, from Galvin, which is extremely popular book for the operating systems. They're saying a thread library provides the programmer with an API for creating and managing threads. So that's what they're saying. The thread library is there, right? To create the threads. There are two primary ways of implementing a thread library. A first approach is to provide thread entirely in the user with no kernel support. Okay, I mean if that is the first approach, then we are calling it user level thread, right? If there is no kernel support, all code and data structure for the library exist in the user space. This means that invoking a function in a library result in a local function call in the user space, not in system call. Okay, so if you're not using system call, then this is the first approach, that is basically user level thread. The second approach to implement kernel level library supported directly by operating system. In this case, code and data structure for the library exists in the kernel space. Invoking a function in API for the library typically result in system call for the kernel. So anyway, this is kernel level thread basically. These are the user level threads. Okay. Now let's just understand this user level threads in more clear way. That what is this user level thread? See, this is our address space, and let's suppose this is one process. Okay, suppose this is one process. This is one process P1. This is another process P2. This is another process P3. Suppose these are the three processes P1, P2, and P3. Now P1 has how many threads? 1, 2, 3. P2 has two threads. P3 has just one thread. Now, interestingly, if it is a user level thread, then all the things are managed by just user program or user library. Okay, okay, everything, whether it is stack, I mean, whether these are registers or anything, which means that CPU for the kernel basically, for the kernel or for the operating system does not even know. It doesn't even know whether these are the three threads. According to the operating system, this is just one process. It doesn't know if this is having the user level thread. Then we see, for to create the user level thread, have we interacted to the kernel? No, right? We are just in the user space. So we have not interacted to the kernel, which means that kernel doesn't even know these are the three threads. Okay. Okay, understood. So similarly for P2, if these are the two threads, kernel doesn't even know these are the two threads. So user level thread look like this. And let me just tell you that if these are the user level threads, okay, if these are the user level threads, then this is okay. If these are the user level threads, then this is what kernel sees, which means kernel will see them just a process. Kernel doesn't know what is inside. Kernel doesn't know what is inside. Kernel doesn't know what is inside. Okay, this is what kernel will see. Let me know if that is understood to everyone. Okay, hope that is okay. Now for the kernel level threads, if these are the three, right? If these are the three, then kernel actually knows. Okay, kernel actually knows these are the three threads. Kernel actually knows these are the two threads. Kernel actually knows this is just one thread in this particular process, right? So I hope you got the difference. See here, kernel knows about these threads. Earlier kernel was just, see, earlier if you noticed, then kernel was just seeing this as a processes, right? But here in the, just a second, yeah, in the kernel thread, kernel knows that these are the multiple threads. Is this okay to everyone? Little bit, right? Okay, okay, maybe you are understanding a little bit. So I can also paste this diagram which is for the kernel threads. So these are the user threads that we have. User threads, these are the kernel threads, right? Great. Now now you tell me, what are the advantages and what are the disadvantages of these kind of threads. Which means if you are having, let's suppose, user level threads, then these are small and fast. Why these are fast? Can anyone tell me? Because system calls are not involved, right? System calls are not involved here. Okay, that's why these are fast. So user level threads are fast because there is no system call involved here. And coming to the user level threads, what is the disadvantage? Disadvantage is that OS does not know about it. Okay, so since OS does not know about it, there is a disadvantage. Why that is a disadvantage? Why that is a disadvantage? Because suppose let's suppose that kernel doesn't know these are the three threads, right? These are the three threads. Now let's suppose these are the two CPUs. Okay, somehow some let's suppose these are the two CPUs, CPU1, CPU2, CPU3. Now let's suppose these two CPUs are idle. In that case, there is no other process. Let's suppose, in that case, do you think these threads can be scheduled differently on different CPUs? No, right? Because kernel doesn't even know these are the multiple threads. So that is why the scheduling decision is not good here. Okay, I will talk more about it. Don't worry. So what are the advantage and disadvantage? Advantage is that it is fast. Disadvantage is that kernel doesn't know. Kernel doesn't know. Hence the scheduling decisions. Okay. Hence kernel cannot schedule them to different CPUs. Right. To different CPUs. Understood? Okay. So see here, advantage, they're fast since no OS element. Disadvantage, OS doesn't know about the threads. So if the thread block, okay, so this is also the disadvantage. I mean, basically, let's suppose there are multiple user level threads, right? Let's suppose this thread is saying that I want to read from disk, which means it is making some IO request, and because of that, this thread is getting blocked. Tell me, can kernel schedule this thread, one of the other thread? If one thread is getting blocked, then can kernel schedule the another thread here on the CPU? What do you think? Can kernel schedule another thread? Answer is no, right? Answer is no. Why? Because kernel doesn't even know that there are multiple threads. So if one is basically blocked, right? If one is blocked, then the entire, okay. So if one is blocked, then the entire process is blocked. So the thread, if one thread is blocked, so what is the disadvantage? If one thread is blocked, then because of IO, then all the threads get blocked. Okay, all the threads get blocked. So this is a major disadvantage, right? Now let's just see what are the advantage and disadvantage of the kernel level threads. The OS provides allusion to each thread. Okay, just a second. So what are the advantages and disadvantages of kernel level threads? Advantage is that it is known to kernel, hence scheduling decision can be efficient, right? Known to kernel, hence scheduling decisions can be efficient. Which means, what do I mean by that? If one thread is getting blocked, okay, one thread block does not mean whole system, whole process is blocked. One thread block does not mean whole process is blocked. What is the disadvantage? It is slow. Okay, it is slow. Understood? Now you tell me why it is slow? Because of system call. Because of syscall. Okay. Now you tell me that let's suppose these are the user level threads. Let me just copy that on the next page and let me just try to explain you what I'm trying to say. Okay, just a second. Yeah. So let's suppose I'm saying here that these are the user level threads. Now, as kernel can't do the scheduling, which means kernel doesn't even know. So kernel will schedule the whole process. Now, out of the whole process, which thread will currently run on the CPU? Can anyone tell me which thread will get executed on the CPU? Which means which thread will get executed on the CPU will be decided by whom? If kernel doesn't even know about the threads, then kernel will schedule the process, right? So kernel will schedule the whole process. So OS will schedule whole process. Now, out of that whole process, which thread will eventually run on the CPU? Who will decide? Now, out of all three threads, which thread will run? Whole process. Let's suppose process name is P1. Who will decide it? Yes, that is called user level scheduler. So basically, there will be the user level scheduler who will decide who is going to run, right? So this decision, I mean, who is going to decide? So basically, there are libraries. You don't need to worry about it, but that's called user level scheduler. User level scheduler will decide. And in case of kernel threads, who will decide? That is actually the real scheduler. I mean, the kernel level scheduler or the operating scheduler will decide, right? Operating system scheduler will decide here. So that's okay. I mean, in this case, the decision that who is going to run, actually this is known to the kernel. So in this case, it will be decided by the operating system scheduler. But here who will decide? The user level scheduler will decide, right? Okay. So let's just see this summary that a single execution stream within the process. That's a thread, right? User level thread may result in kernel making a poor scheduling decision, resulting in the slower process execution than if the kernel were used. So basically, user level schedule threads may result in the poor scheduling decisions. Okay. Okay. So we will see the PYQs also. Don't worry. Okay. Now let's just see few questions. Let's just see this question. What they're saying: the OS provides illusion to each thread that it has its own address space. What do you think? Do OS provide illusion that it has its own address space? Or it says that, okay, that it, I mean, do OS says that it has every thread its own address space, or it says that address space is actually shared? Let me know. So it says that address space is actually shared, right? Great. So basically there is just one address space, as we have talked. So let me just go to that particular slide. See here. See, if these are the multiple threads, then also the whole address space is same, right? Whole address space is same. So there is just one address space. Do you think that OS provides the illusion that these are the multiple address spaces? Then the answer is no. Okay, then the answer is no. Let me know if that is okay to everyone. Okay. Okay. Now let's just answer this question. Let's just answer this question. Let me go to that question. Okay. And before that, can you tell me whether this is true or false? The kernel level threads, multiple threads from the same process can be scheduled on the multiple CPUs simultaneously. So this is true, right? This is true. Okay. Can you answer this gate PYQ that has been asked in 2011? So what they're saying, a thread is usually defined as a lightweight process because an operating system maintains a smaller data structure for the thread than the process. In a relation to this, which of the following statements is correct? Okay. OS maintain only scheduling and accounting information for each thread. Accounting information means that what is the stack pointer. So basically, if you have noticed that each thread has its own stack pointer and these things, right? So see here. Uh, I think, yeah. So each thread has its own stack pointer and these things, right? So if the thread is visible, if the thread is visible to the operating system, then operating system will be maintaining these data structures. So basically in this question, can you first tell me that are they talking about the kernel level threads, or they are talking about the user level threads? If OS is maintaining some data structure, or OS is doing something for some thread, then it means they're talking about the kernel level threads, isn't it? They're talking about kernel level threads. Why? Because for the user level threads, OS doesn't do anything. If OS has to maintain the smallest data structure or whatever, right, then it is kernel level thread. Now OS maintain only scheduling and accounting information for each thread. OS maintain only CPU registers. No, OS maintain everything, right? CPU register. Accounting information means that like where is the stack pointer, where is the program pointer, and these things, right? OS maintains only CPU registers. No, I mean it also maintains that, okay, stack pointer, these things. OS does not maintain virtual memory state. Yeah, it doesn't maintain this. Why that is the case? Why that is the case? Can anyone tell me? Because just the question that we have done, right? The OS provides an illusion that all the threads have the same address space. Since all the threads has same address space, that is why the virtual memory or the address space is, by the way, same, right? Virtual memory means, virtual memory state means, it actually means the address space basically, right? Okay, so OS does not maintain address space for each thread. Yes, that is true. Okay, it does not maintain address space for each thread because that is just one address space. See, many of the aspirants doesn't even understand that it is actually talking about the kernel thread. Okay, they do not answer these questions confidently, right? They do not know that they're talking about the kernel thread. Now you tell me, have you understood this question correctly? And can you answer this confidently that they are talking about the kernel thread? Right? Okay. Just answer this question. If a user level thread is blocked for IO operation, then kernel OS will perform context switching to another user level thread which is not blocked. I mean, it will schedule another user level thread. Do you think this? Do you think that it will schedule another user level thread? Just let me know. Answer is no, right? Answer is no. So this is basically, I can say this is false. What about this? Many to, okay. I will talk about this many to one and these things. Okay. Before that, can you answer this question? Context switch means just scheduling. Okay, I mean scheduling the next thread. We will see the context switch in more detail, but for now, just treat it just like a scheduling. Consider the following statement about the user level thread and the kernel level threads, which is false. So they're asking about the false. Context switch time is longer. Okay, currently we have not seen this, so we will see this. Okay, I will come back to this in a minute. Okay, I will come back to this. So don't worry, I will come back to that particular point. Now for now let's just see first that what are the multi-threading models. Okay, what are the multi-threading models? So have you understood that there are user threads, right? That OS doesn't know. OS just sees that, okay, for OS it is just one process. There are kernel level threads for which OS knows everything, right? Okay. Now let's just see these models, that what is this many to one, one to many, many to many. Okay, let's just see these models. Tell me, before I tell you these models, tell me what are the advantages and disadvantages of kernel level and user level. So let's suppose I write user level. Here I write kernel level. So can I say it is fast? Can I say it is slow? Can I say that if one thread is blocked, if one is blocked, then the process is blocked? Here and here, can I say if one is blocked, then process is at least not blocked, right? Then process is not blocked. Not blocked if there are multiple threads, obviously. If there are multiple threads in the process, right? If there are multiple threads. Is this okay to everyone? Writing like this? Let me know. Let me know if that is fine. Okay. Okay. So basically, if we have like user level thread, then it is fast and it is slow. So there are advantage and disadvantages both. So which one will you prefer? Can you tell me? So can you say that you will prefer the user level thread, or can you say you will prefer kernel level thread or something like this? Which one you will prefer? So since it is hard to choose that which one to prefer, that's why we have the hybrid models. Okay. So it is hard to choose that which one to prefer. Okay. It is hard, hard to choose that which one should prefer, right? Which one is preferred. and hence we have multiple ideas here which are many to one to many, or many to many. So these are called many to one means many user level threads are mapped to one kernel level thread. One to one means one kernel or one user level thread. One user level thread is mapped to one kernel level thread. Mapped to one kernel level thread, right? Many to many means many user level are mapped to, let's suppose, many kernel levels, right? So let me just explain you that what are these. So this is called hybrid model. For example, let's suppose you write a program. In that program, let's suppose this is your program. Here you have multiple user level threads. Okay, let's suppose these are the 6 user level threads. Now suppose you somehow know, that these two threads should you can say, like, let's suppose you know that if you run these two threads, then you can basically, if this is one of them is blocked, then maybe it is okay that this is also get blocked, right? It is okay if one of them is blocked, then it is also getting blocked, which means you don't want to run them in the parallel, let's suppose. Somehow see, you are the programmer, isn't it? So as a programmer, this is your program, right? This is not my program, this is your program. And since it is your program, you might be knowing that, okay, these two threads, maybe you can treat these two threads as a just one kernel thread. Okay, so what do I mean by that? What we can do as a programmer, we can say that, okay, these two threads, or maybe these 4 threads, I'm saying that, let's just say this is one kernel thread. Okay, one kernel thread. This is another kernel thread, which means, okay, let's suppose this is another kernel thread, which means what? It means that kernel, as per the kernel, how many threads are there in this program? As per the kernel, how many threads are there in this program? Only 3 threads, right? As per the kernel, only 3 threads. So how to make this grouping? This is using again the libraries. Okay, you don't need to worry about it. Okay, this is again using the libraries. You don't need to worry about it. So basically, you can group them using the library, and you can say all of these user level threads, it's just one kernel thread. This is one kernel thread. This is another kernel thread. So this is called many to one mapping. Many to one mapping. Okay. This is called many to one mapping. Is this understood to everyone? That many user level threads are mapping to just one kernel thread. And now consider the scenario where if I'm saying that maybe if I'm saying that each of this user level thread is just one kernel thread. Okay, then it is which kind of mapping? Is separate kernel thread, one to one, right? And similarly I can have one to many, which means I can say, okay, using the libraries, that this thread is basically multiple kernel threads. So you can run this particular code simultaneously at the multiple CPUs basically, right? Okay, so you can have one to many also. You can have one to many. So these are the many different kind of modeling possible. Okay, sorry, many. Okay, not this. What I mean. See, we have seen one to one. We have seen many to one, right? Many to one generally basically mean that that all of them. Okay, So for example, this all of them is basically mapping to one. So it is called many to one. So many to, in general, there is called many to many also. Many to many means, it basically means that these four are mapping to, for example, three threads. Okay, three kernel threads, three kernel threads. So this is called many to many. I mean, many are mapping to many. Okay, and these two are maybe mapping to just one. Doesn't matter. Okay, so these are many. Not are, they are not mapping to just one. Maybe many to many also. Okay, many to many also. So don't you think it's a good idea to have this kind of hybrid? Suppose if you make it a proper use, okay, and you know that okay, these two threads can be blocked. Okay, I mean, if this is getting blocked, then it is okay to block this because you don't want to run them in parallel. Then isn't it a good wise idea to make these two threads as a one kernel thread? Because if one of them is blocked, then already another one is blocked. Suppose as a programmer, you know that your code is written in such a way that even if this is blocked, then it is okay to block this. Isn't it a good idea to optimize the things that instead of saying all of them are kernel threads or something, or all of the, combinedly all of them are kernel threads, instead of saying that, or individually each of them is kernel thread, isn't it a good idea to say that these two combinedly one kernel thread? Okay, if you somehow can make this intelligent decision. Mapping means that for one kernel thread, okay, I mean, kernel will see that, okay, kernel will see that these two are just one thread. And now user will be deciding that which thread to execute on the CPU. I mean, user level thread will at a time, it will map one of the thread to this kernel thread. Okay, so don't worry about it. Maybe this is little complex to understand, but I'm trying to make it little easy. So let's just understand from the directly from the standard textbooks. So let's just try to read from the Tenenbaum. See, this is the only paragraph that Tenenbaum has for this hybrid implementation. Similarly, I have also seen William Stalling. This is the only paragraph that William Stalling has this for this hybrid implementation or this mapping. Similarly, I have also seen Galvin, and this is the only paragraph that Galvin has. So I have taken from all the resources. Okay, maybe we can read one of them. Okay, maybe we can read one of them. So let's just read only Galvin. Okay. So our discussion so far has been treated thread in a generic case. However, support for the thread may be provided either at the user level, user thread, or kernel threads. User threads are supported above and the kernel are managed without the kernel support, whereas, okay, this is okay. Ultimately, a relationship must exist between the user and kernel threads. In this section, we look at the three common ways of, okay, so they are saying there are three common ways of establishing them. Now, I think, yeah. So in the Galvin, basically, I think these are the diagrams, right? So these user level threads are mapping to one kernel thread and so on. Maybe we can read from William Stalling first. So they are saying some operating system provide a combined approach for user level thread and kernel level thread facility. In a combined system, thread creation is done completely in user space. As in the bulk of scheduling and a synchronization of thread between the application, the multiple user level threads from a single application are mapped onto smaller or equal. Okay, so multiple user level threads are mapped to smaller or equal, which means four user level threads can map to three or four, but not five. Okay, smaller or equal number of kernel level threads. The programmer may adjust the number of kernel level threads for a particular application and process to activate the best overall result. In a combined approach, multiple threads within the same application can run in parallel on a multiple processor or on the multiple CPUs, and a blocking thread call need not to block the entire process if properly designed. See, the key idea here is that if properly designed, if you really know that, okay, if you map, let's suppose you really know that if you map all of this as one kernel thread, then it is very good. Okay, if properly designed, this approach should combine the advantages of both pure user level thread and pure kernel level thread. Okay, so it is only the thing that it is properly designed or not. Okay, if properly designed, then you can take the advantage of both. Understood? Okay, so maybe now you understood that what does this mapping mean, right? What does this mapping mean? Now, let's just move to the next topic, which is context switching. This is a small topic, but before that, I want you to make sure that everything is clear to everyone. Let me know. Let me know if there is any doubt in the mapping. Okay. Okay. So let's just move to the new topic, which is context switching. It is a small topic only, right? It is very small topic. So suppose there are multiple processes that want to get scheduled on the single CPU. Okay, so everyone is fighting for just single CPU. Now how to make the context switch? Let me just tell you. So suppose in the CPU, I mean, this is, let's suppose, process 1, this is process 2. This R1, R2, R3, these are the general purpose registers, and these are the CPU registers, right? Let's suppose it is working with R1, R2, and suddenly you want to schedule some other process, right? Suddenly you want to you want to schedule this P2. Tell me, can you use the same values of R1, R2 here? Or should the R1, R2 be not used? I mean, can you use the same R1, R2? Let's suppose you are saying, okay, move this 100 to R1, and R2 is containing 200, right? And now after that, let's suppose you want to execute this. Okay, you are at this stage, you want to execute this. Can you say that, okay, this 100 plus 200 should be added, or this 400 plus 500 should be added? Obviously 400 plus 500 should be added. So basically, whenever you are making a switch from one process to another process, it is called context switch, and in that case we need to save the registers in the memory, right? And then whenever we are coming back, we need to restore them from the memory. Okay, we need to restore them from the memory. So this is called context switch. But let's just try to understand this context switch in the more detail. Okay, so context switch basically save the state of the process before switching to another process, restore the original process state when switching back. So it is a simple concept, but okay, but what is this but? How do you save? How do you stop the execution? How do you restart the execution of the process? So let's just understand this completely. Okay, let's just understand this context switch completely. Now let's suppose that you have your virtual memory or address space. Do you remember that your address space looks something like this, where, I mean, we call it OS, this is heap, this is stack, this is data, this is something, right? Now in operating system, for every process, see, this is an address space of one process, right? This is address space of one process. So for every process, there is a kernel stack. Okay, for every process, I mean, this operating system maintains some memory which is called kernel stack. Just like the user stack, you also have the kernel stack. Okay, you also have the kernel stack. Now let's just see that what do I mean by this kernel stack. See, you have two stacks for every process. Okay, two stacks for every process. One is called user stack, one is called kernel stack. Now why they are used, let me tell you. See, suppose you are executing P1, but you are executing this P1, you can execute this P1 or some process, right, either in user mode, and maybe because of system call you are executing this only, but because of system call you went to the kernel mode. Okay, you went to the kernel mode. So now you are executing this process in the kernel mode, which means this P1 was there, you are executing in the user mode only, right? Now because of some system call, okay, because of some system call you went to the kernel mode. Okay, maybe because of some reason, and here you are executing, I mean, you are executing some program, right? You may be executing some program in the kernel mode. Now in the kernel mode, let's suppose if you want to push, or if you want to okay, let me just take you the example. In the user mode, let's suppose if you want to push some global variable, or sorry, some local variable, then you will be pushing in the user stack, right? Now if you are in the kernel mode and if you are executing the same program P1, okay, in the kernel mode you can execute any program basically. Let's suppose you are executing the same program P1, then you will be pushing the variables in the kernel stack. Generally, it is not basically very popular. It is not being used also for this purpose, but it is being used for other purpose, which means, let's suppose, let me just tell you that what are these user stack and kernel stack. Why do we switch from user stack to kernel stack when we enter in the... Okay. Suppose, see here that you are basically let's suppose in the user mode, and now you want to store I mean, you want to go to the kernel mode and you want to store your program counter value, stack pointer value, and these things, right? Where will you store this? Where you will store the program counter, stack pointer of some program, let's suppose P1. Where you will store? You will store all of these values in the kernel stack of P1. Okay, we will store okay. So assume that you are in the you are executing this, but you are going to some other process, right? You are going to some other process. So you want to store all of the metadata, then you will be storing in the kernel stack of the P1. Now let's suppose, my question is that, suppose consider a case where we have just one kernel stack for all the processes. Then what will happen? Suppose you are having just one kernel stack. So let me just tell you that what's going to happen here. Here, see, this is, let's suppose, a kernel stack for all the processes, right? Kernel stack for all the processes. Now you will be doing what? You will be basically let's suppose switching from P1 to someone, right? So you will be storing P1 context here, P1 context. Now you are executing currently someone else, and now let's suppose you are executing P2, and then you will be storing P2 context. Then maybe from P2 you went to P3, now you are storing P3 context. Is this understood to everyone that what do I mean by that? That suppose there is only one kernel stack, and in the kernel stack, as I told you, you will be storing the context, right? So you are storing P1 context, I mean the stack pointer, these things, right? P2 context, P3 context, and so on, right? Why that is the case? Because you were executing P1, but then you switched, okay, switched to P2, and then you switched to P3. Okay, I mean from P2 you went to P3, and now you switch from P3 to someone else, okay, to someone else. So that is why I had to push the context here. I had to push the context here, and so on. Is this okay to everyone that what I'm trying to say here? Now suppose at this moment in time, you decide that, okay, let me wake up this P1, or maybe let me schedule this P1. This is CPU. Now can you schedule this P1? If you want to schedule this P1, then you have to use this context. Okay, you have to use this context. So if you schedule this P1, then you have to pop out all of this, right? Is this possible to pop out all of this? I mean, it is possible, but don't you think it is very, very unnecessary to pop out all of this and then push it again and then save it to some other thing, and it will be too much hectic, right? So what I'm trying to say, if you have just one kernel stack, then you can't just schedule on CPU in any way, which means if you are blocking P1 and then you are blocking P2, then you are blocking P3. Then you have to unblock P3 because P3 context is on the head, right, on the top. Then you have to unblock P2, then you have to unblock P1. No, these are not threads, these are the processes. What I'm saying, that these contexts of these processes have to be pushed in the kernel stack, right? I'm assuming that there is only one kernel stack. In that case, P1 will be pushed here, P2 will be pushed here, P3 will be pushed here. Now, if you want to unblock or if you want to use this P1 context, then you can't do without popping out this. So that is why if there is only one kernel stack, then the order have to be maintained. If we are blocking in this way, then unblocking should also be in this way, isn't it? Let me know. Let me know if that is clear to everyone. So that is a problem in having. I mean, it's not like that it can't be practical or it can't be implemented, but it is a problem in having one kernel stack. So that is why we have multiple kernel stacks. So I will be pushing P1 context here, P2 context here, and so on. Okay, I will be pushing these contexts like this. Now let's see this question. What this question is saying: why do we switch from user stack to kernel stack when we enter in the kernel? Why do we associate unique kernel for each thread? So they are basically asking why do we associate unique kernel for each thread. Let's just see answer. Okay, so basically why we basically push on the kernel stack, because we don't want to push on the user stack. Why? See, I can push the context on the user stack itself. Okay, but I don't want to push the context on the user stack because I don't trust user. Maybe they may modify the values, right? They may modify the values, and I don't have any in the user stack. User can modify the values without asking the operating system, because that's in the user mode. I will be executing all of this in the user mode. So that's why I have the kernel stack. This is the answer of the first question. The next question is that why do we have the unique kernel stack? Now can you answer why do we have unique kernel stack? The reason is that for the unique kernel stack for each thread is so that kernel can put threads to sleep simply by unloading the threads register into TCB and putting TCB on the wait list. When we wake up thread later, it can continue exactly where it left off. So basically if you want to block it, you can directly block it, and if you want to unblock it, you can continue directly. Basically it's not like that. You don't have to follow the order, right? If there is only one kernel stack, then you have to follow the order P1, P2, P3. If in this order you are basically putting, then you have to first execute P3, then P2, then P1. Okay, maybe we can see one more question. Okay, so I think that question I don't have, maybe. Okay, let's not worry about it. Okay, let's not worry about it. But let's just see. There was one question that I was thinking that I have, but let's not worry about. Let's just see the context switch directly. Okay, what is this context switch? So I hope this process stacks are okay to everyone. That there is a kernel stack and there is a user stack for the processor, and there is a kernel stack for the processor. So every process, okay, again every process has two stacks. Is this necessary? I mean, is this very necessary? Can't you just have only one kernel stack for all the processes? You can, but it will be difficult to maintain. I mean, it will be basically difficult. I mean, for the execution, you need to pop out all of this to execute to execute any of this you want to, right? So basically, you can maintain only one kernel stack, but it is feasible to have multiple unique kernel stack for every process. So it is good to have two stacks for every process. Okay. Now, maybe if you want, you can just read out it later on. Each process has a kernel stack, or more generally, each thread has its own stack. You can read out it later on. Okay, you can read out it later on. The kernel stack of the currently running process or thread is used by the interrupt handlers. So maybe you can read out it later on. It's a good paragraph. Okay, if you want to read out. Now let's just see the context switch directly. Okay, how the context switch is happening. So basically it is P1 and P2. So I want to switch from P1 to P2. Let's just see how it is happening. Let's suppose you are executing P1 code, and then maybe because of some reason. What could be the reason? Maybe system call has been there. Okay, this could be one reason. Maybe user has pressed some key and you have got the interrupt. The interrupt you might be knowing, but that is a part of computer architecture. So basically, if there is an interrupt, then also you will be resuming the P1 execution. Okay, so maybe there is a system call, maybe there is an interrupt, or what else can happen for which I need to block this P1. Maybe the timer got expire. So there could be multiple reason that you want to resume. Okay, you want to pause the execution of P1. Okay, so pause execution of P1 in all of these cases. Now suppose this is P1, this is, and then you want to schedule, let's suppose, P2. So let me just tell you that how the scheduling is happening, right? So see, some, like, you are executing P1 and then something happened. Okay, what that something can happen? What is that something that may can happen? The something is basically system call, interrupt, timer can get expired if you're using round robin scheduling. So there are many possibilities that can happen. And then from this P1, you will say, okay, let me go to kernel mode because of these things. Okay, these things are basically the only reason to go to the kernel mode. If someone asks you that what are the possibility in which we can go to kernel mode, either system call or interrupt. I mean, timer is also hardware interrupt, it doesn't matter. So basically, system call or interrupt, only for these reasons you can go to the kernel mode. Okay, so basically you will go to the kernel mode. Still, I mean, you are going to the kernel mode. Now you tell me, okay, once you go to the kernel mode, you are executing, you are basically currently executing P1 or someone else. In the kernel mode itself also, you are currently executing P1. Okay, so you are saying you are basically executing P1 in user mode. Then something happened. Okay, something happened. Okay, something, what are these something? System call, interrupt, or these things, right? Something happened, and then you will be executing P1 itself in kernel mode. I mean, currently you have not switched it. Okay, currently you have not switched it. So now still you are basically executing P1 in the kernel mode, and then you will set the mode bit. Okay, to be maybe or maybe before that itself you will be setting the mode bit to be 0, right? So something happened, and maybe you can say that mode bit, I can set it to be 0 in the user mode or in the kernel mode. That I think it should be modified in the kernel mode itself, right? Mode bit to be 0. And then what will happen next? See, you want to schedule, let's suppose, P2. Then the next thing that will happen is basically you will say that, okay, let me store P1 context in P1 kernel stack, isn't it? So this is the next thing that will happen. Okay, let me just write it on this side. Yeah, so this store is basically, PCB is just a data structure, so PCB will get update basically, right? So you will store that context, and in the PCB also you will update the PCB will get updated, which means PCB will be having a stack pointer value, maybe program counter value. These will get updated, that okay, these are the PCB values, right? Okay, okay. Now you are in P1. You went to the kernel. I mean, you stored here. Now currently still you are executing P1, right? Will you directly switch to P2 from P1? I mean, from P1 is in the kernel mode still. Still P1 is in the kernel mode. Will you directly switch to P2? No. There will be some scheduler, OS scheduler, that you will call, right? OS scheduler will get called, and OS scheduler will do what? It will say that, okay, I want to execute to P2. Then this P2 will get scheduled, and then P2 context will be restored from the kernel stack, and then you will start executing P2. So maybe I can write the whole flow. So basically, step 1, P1 in user mode, and then you went to P1 in kernel mode. and then store p1 context in p1 kernel stack, and then start schedule the scheduler itself, right? I mean, the scheduler will get run, and then it will schedule p2, and then this p2 context, right? P2 context will get stored, will get restored basically from p2 kernel stack, right? And then uh, you will set mode to 1, and you will say start executing p2, right? So these are the steps. Now can you tell me the context switching which is really happening here, right? Really happening after this, it is in the kernel mode or the context switch happening in the user mode? Tell me. The context switching, if someone asks you that context switch happens in user mode, this is true or false? Tell me. This is actually false. This is false. Context switching really happening in the kernel mode. Okay, in the kernel mode you have this store, you will store the p1 context, and then you will do the context switching. Okay, I mean really you are switching in the kernel mode actually. Okay, so now let's just see more questions. The user stack and the kernel stack for the given process are located in the same page in the physical memory. I mean, same page means same frame. Okay, you might be knowing about the frame from the memory management. Little bit you might be knowing. If you know, then you can answer this question. Tell me if you know. Do they have to be in the same frame? No, these are the, I mean, user stack is somewhere here, kernel stack is somewhere here, right? Maybe these are the two different, or maybe it is after 5 frames or 10 frames, right? So no. If you know it, know the frames, what is this frame, then you can answer. Otherwise, you can leave it for now. Okay. Context switch only happens when the process already in the kernel mode. This is true or false? This is true, right? This is true. Okay. Now let's just see thread context switch versus process context switch. So basically, let me just tell you, user, if you're context switching between user threads context switch, kernel threads context switch, kernel threads of the same process basically, right? I mean user threads obviously of the same process. I'm talking whenever I'm talking about the threads basically of the same process. Okay, of same process context switch, kernel threads of same process context switch, and two different processes context switch. Let's just talk about these two things. Okay, these three things, two different processes context switch. Let's just talk about these three things. Which one you think is the fastest one? See, user thread context switch, do you really think it's a context switch? I mean we should not even call it a context switch, because I mean that's in the user space only, right? We are not even dealing with the kernel stack, or the kernel is not even involved here. So this is the fastest one. Okay, I mean kernel is not even involved. This is the fastest one. Okay, this is faster than the process context switch. Can anyone tell me why? Kernel threads context switch is faster than two different processes. Can anyone tell me why? Because see, if you are having two different process context switch, in that case, if you are little bit familiar about the page table and all, okay, then you have to modify the page table base register. There is a register that contains the page table base. Okay, you might be little bit familiar about it, that there is something called as page table base register, and that has to be modified if address space is changed, or maybe if the process is changed, right? If the process is changed. So if you're having the context switch between two different processes, then you need to modify the page table base registers also. So basically this has, whatever you do in two, right? Whatever we do in two plus page table base registers plus something, maybe something extra, right? Which are very process specific. Okay. So basically, let me just summarize you that out of these three, why first is fastest one, and then second, and then third. So you can say in terms of speed, okay, speed, or okay, let me just use the term speed. One is the greatest speed or the fastest. Basically, you can say fastest. Okay, then two, then three is the slowest. Can you tell me why that is the case? Why one is fastest? Because kernel is not even involved, no system call. Okay, only using the function call you can do it. Why two is little faster than the third? Because in the third you have to do all the things which two does, plus page table base registers, plus something which are very specific to processes, right? Maybe you need to flush the TLB, because TLB is also the process specific. Okay, let's not worry about the details, but maybe you need to flush the TLB also. Okay, plus maybe flush TLB. Basically TLB is a virtual to physical address translation, right? So if the processes itself is changing, then maybe we need to flush the TLB also, right? Or invalidate the TLB or something like that. So basically these three order is very important to understand, and you won't believe there are multiple gate question has been asked on this. Okay, multiple gate PYQs on this, on this concept. Multiple. Let me just show you. Okay, let me just show you what are those gate PYQs. So basically on this concept there are multiple gate PYQs, that one is fastest, two is slower, three is slowest. Before I go to the gate PYQs, can you just confirm if you're understanding that why this is fastest? Why one is fastest? Because the kernel system call is not even involved. Kernel threads are little slower because compared to the two different processes, because processes has to do many more things than only the kernel threads. For example, thread context switch versus context process see the thread context switch, actually it is not really important for this question, but whenever they say context switch thread, then they really mean the kernel thread. Okay, kernel thread. सो एक्चुअली यूजर थ्रेड के कॉन्टेक्स्ट स्विच को तो कॉन्टेक्स्ट स्विच भी नहीं बोला जा रहा है, ठीक है? वो इतना ज़्यादा फास्ट है, वो कर्नल को पता भी नहीं है ना, तो यूजर थ्रेड का अगर कॉन्टेक्स्ट स्विच भी हो रहा है तो उसको कॉन्टेक्स्ट स्विच भी नहीं बोलते लोग. ओके, दिस इज जस्ट अ टर्मिनोलॉजी, नॉट एवरीवेयर, बट आई एम जस्ट टेलिंग यू. ओके, so see, maybe you can read this. The main distinction between the thread context switch, or the thread means kernel thread, and the process switch is that during a thread switch, the virtual memory space remains same, right? The address space is same. This is the main important point. The address space is same, while it does not during the process switch. Okay, this is because of this. Okay, the TLB flush may be there. Okay, page table registers may be there, or something like this, right? Okay, cost of switching out the registers, and the registers is the largest cost, and so on, right? You can read this paragraph later on. I'm just telling you that there are 238 upvotes. So this is a very nice answer, right? So let's just see this Berkeley question. What they're saying: what needs to be saved and restored on the context switch between the two threads? Okay, if these are the two threads, then what we need to, save and restore. So basically, thread context switch means two. They generally mean the kernel threads. Okay, it means the kernel threads in the same process. And what if two threads are different process? So they are saying that if you are switching kernel threads of the same process, or you are switching between two processes, okay, then need to save the process registers stack pointer in these things in the thread control block or the process control block, whatever you want to say. And when we have two different processes, then need to only save and restore what was given above. Need to not only save, okay, not only save what is above, which means, let's suppose this is 2, okay, I told you, right? 3 equal to 2 plus something page table based registers and these things, right? So that's what they are saying. Not only save and restore what was given above, but also need to load the pointer to the top level page, yeah, page table based register and these things, right? The things which are process specific. Now, have you understood crystal clear way that why 1 is fastest because no system call, why 2 is little faster than the 3 because 3 is 2 plus something extra, which is page table register, maybe flashing the TLV and so on, okay? Yes, if we are, so Satyam is asking, does kernel level thread context switch require a change of mode bit? Yes, definitely, because you will be basically using the system call because kernel is involved. So if the kernel is involved, you need to change the mode bit. Now let's see this gate question. Tell me what is the answer. What they are saying with respect to user level threads and kernel supported threads. Context switch is faster with the kernel supported threads. For user level threads, the system call can block the entire process. So context switch, do you think context switch is faster with the kernel level threads if you compare kernel and user level thread? What do you think? What do you think? Let me know your answers. Then only I will get to understand whether you are actually understanding the things or not. Let me know your answer. That this is true or false. If you compare user level and kernel level context switch, this is true or false. This is false, right? This is false. Great. Great. For user level threads, the system call can block the entire process. Yes, this is true. If one thread is blocked, then entire process is blocked. Kernel supported threads can be scheduled independently. Yes. Yes, this is also true. User level threads are transparent to kernel. Okay. So what does this transparent mean? So they are saying user level threads. Tell me what does this transparent mean? Actually, transparent means here, interestingly, this is English language and it is sometimes very tricky also. Transparent basically here means that it is not visible actually. Okay, the transparent mean that kernel can't see them. Okay, so I know it is a bit tricky to understand, but here the word transparent. Okay, you can just Google it out. That let me just tell you that what does the Google says. User level threads are transparent. So here the word transparent basically means that it is not visible. Okay, so see, let me first tell you that what does this transparent generally, it is just an English language, don't worry about it if it is problem to you. So see here, this paragraph says here actually generally it is taken, okay, it is taken transparent is visible, but it is it is opposite of that, okay. kernel level threads are not transparent to kernel, but user level threads are. Okay, so because you yourself said user level threads are managed by user level library, and what happens if the user level thread can get assigned one or more kernel level thread? About these kernel threads are kernel keep track of that are not transparent to kernel. Okay, transparent means that, so basically let's suppose this is kernel level threads, right? So I mean, I'm just trying to interpret this English language, and let's suppose this is kernel. Transparent means कि kernel को पता भी नहीं चलता है कि कितनी thread है. Okay, so kernel doesn't even know. It get transparent to the kernel. Okay, so they actually mean this. It get transparent to the kernel. Kernel doesn't even know that how many threads are there. So what kind of threads these are which are transparent to the kernel? Which are user threads. It is just an English language. Don't worry about. There is no concept involved here. It is just of English tweak. Okay. Transparent here means that if these are the user level threads which are transparent to the kernel doesn't even know कि कितनी user level thread है. Okay, they get transparent to the kernel. Okay, so this is actually just an English word. Okay, which is making it tricky. So is this true or false? So yes, they are transparent, right? So that's why it is true. So second, third, and fourth are true. So that's why A is the answer, right? Okay. So basically, don't worry about whether you are understanding the word transparent or not. Actually, transparent word here basically means that it is actually transparent. Okay. So kernel doesn't see it. Little tricky as per the English language. Okay. It is no operating system as per the concept is involved. Okay. So yeah, answer is A. Let me know. Have you understood this question crystal clear way? In crystal clear way, have you understood this question or not? See, context switch is faster. Yes, we have understood this, that why it is faster in the kernel supported threads, right? Oh, sorry, why it is not faster. Okay, for user threads, it can block. Okay, kernel supported threads can be scheduled independently. All of this we have discussed in very, very nice way, right? All of this we have discussed in very nice way already. So that's why you should be able to attempt it quickly. Okay, now let's just see this. Consider the following statement about the user level and kernel level threads. Which of the following is false? Context switch time. Okay, again, user level and kernel level threads they ask. Context switch time is longer for the kernel level threads than user level threads. Yes, that is true actually. Context switch time is actually longer, right? True. User level threads do not need any hardware support. What do you think? User level threads do not need any hardware support. Let me know what is the answer of this question. Do you think you can run them in air? You can run without CPU? I mean, sorry, here the hardware support basically mean maybe they mean that okay, registers and all, right? I mean, see, the user level threads do not need any hardware here basically means the registers and all, right? So do you really need registers, or since it is a user level threads, so we can store context in variables, right? In programming variables basically. Okay, which means let's suppose I want to store program counter value. Maybe I can store in some integer pointer or something, right? So I don't really need any registers as such. Okay, so I don't need it. Okay, the hardware, the registers, I don't need it. So that's why it is also true. Related kernel level threads can be scheduled on a different processors or multi. Yeah, that is true. Blocking kernel level threads block all the threads. No, that is false, right? Okay, so yeah, so basically D is the correct answer here. Now let's solve this question. Okay, I think this we have already done. Okay, we have already done this accounting information and these things, right? We have done this. Great. Cool. So that is all. That is all I wanted to discuss here. That is all I wanted to discuss in this particular session. So we have seen in very crystal clear way that what is system call, what are these threads, right? In very clear way, we have understood what is this context switch, right? What is this context switch? And here in threads, we have seen very clearly mappings, right? Mappings we have seen in context switch in very great detail. In a great detail, we have seen what is the context switch, right? System call also in a great detail. Let me know if there is any, if there is any issue here. I mean, have you understood everything or there is any issue? Let me know. Okay, great. If you have really understood well, please just spend. It will just take 1 minute. Okay, please share your comment. It really motivate us. Okay, it really motivate us. If you've understood everything very very clearly as you guys are saying, then please just let me know in the comment. Okay, okay. Please just let me know in the comment. Okay. I mean, basically, after this video end, just let me know so that it really get or like we really get motivated. I mean, many of you are saying that okay, it was a wonderful session, but just comment these things. Okay, just comment. Okay, after the video end. Okay, under the video. Yes, there will be back to back OS revision. Okay, okay, there will be back to back OS revision. Yes, I will be taking paging and all. I will be taking paging and all. So please share your comment under the video. It really motivates us. Okay. So just after, okay, after 1 minute only, after 1 minute, just after this video end, just comment it out, right? Okay. So thank you everyone. Thank you so much for joining for such a long hour. I really appreciate you guys. Okay. I really appreciate. Thank you so much. Take care. Take care. Bye bye.